Hello everybody and welcome to the first CDT-CMP online annual conference. I'm sure this is going to be a new experience for us all, and we've got some new features in our conference: electronic breakout sessions and electronic voting for the best talks and posters. So please remember which talks you liked. Later on we're going to have some voting on that. I'd just like to share my screen for a sec. Okay, does that work?
Yeah,
so
it's not in full screen mode, but it's, yeah, you can see it. There you go.
So just a few etiquettes for the meeting, which I'm sure you all know. So since there's so many of us, as you can see, you've done this already. Switch off your microphones when not speaking. If you'd like to ask questions at the end of the talk, please use the chat function just to say that you want to ask a question and chat with the chair. And please stay logged on all day because Tom is going to do some jiggery-pokery and make people co-hosts to allow them to move through the poster sessions later on. Finally, there's some nice instructions about how to do the poster sessions, but one thing that caught us when we were testing them is moving out of the breakout rooms. You might think that you should click the button that says leave room to go out of the breakout room. Just do not do this, because you'll find yourself in sort of oblivion, and then you have to get Tom to let you back into the real world. What you need to do is to click the button that says breakout rooms again to get out of the breakout room. So that's described in the program. If you do have problems throughout the day with the Zoom, then email the CDT email address, CDT-CMP. Okay, so I'm going to stop sharing and pass over to Simon, who's going to chair the first session.
Okay, thank you, Stephen. Good morning, everybody. So just to remind you what Stephen said, I'll be monitoring the chat line. If you have a question for the speakers, then just post something there to indicate that you want to ask a question, and then I'll invite you to unmute your microphone at some point. So our first talk is from Alex Petkov at the University of Bristol. Alex, are you ready to go?
Yeah, hiya. Can you hear me?
We can hear you. Do you want to share your screen?
Yes. Okay, let's go with this. As soon as it loads.
Okay, okay, good.
Yeah, can you
so
see
Alex's talk is entitled Thin Film Gallium Oxide Deposition from Liquid Gallium Droplets, Substrate Interfaces for Better Thermal Transport. Take it away, Alex.
Thank you. So I'm just going to go briefly to an overview of what my talk is going to be about. So first going to talk a bit about why we're interested in gallium oxide. Why is it relevant in applications for high voltages? What do we mean by better thermal transport? What do we actually want to achieve? Then I'll talk a bit more about the method. How do I produce thin film deposition of gallium oxide from liquid gallium droplets? I'll talk a bit about some measurements that I've taken, mostly gallium oxide to substrate band alignment calculations, and then I'll talk about the future direction of this work and what more needs to be done. So to start off with a bit of background, we know that semiconductors such as silicon carbide and gallium nitride are well used in industry for high voltage switching and power amplification. However, they do have their limit, and the next phase in expanding use of high voltage would be devices that can reliably operate over the limits of silicon carbide and gallium nitride into the range of tens of kilovolts. What this could allow us to do is better operation and less loss in power transmission lines in data centers and faster charging of electric vehicles. So here is where gallium oxide comes in. It's it's beta phase, which is the most relevant, really. It's the most stable out of all of the other ones. It's a monoclinic crystal. You can see it's unit cell. Why is it so interesting and so attractive? Well, first of all, it's really easy to create large crystals from melt. It has a very high breakdown field of 8 megavolts per centimeter, which means that it can easily withstand huge voltages. The main downside to this material is its poor thermal conductivity, which only goes to up to 27 watts per meter per Kelvin. The thermal conductivity is anisotropic, and this is in the 010 direction. It's the highest one. The other ones are even lower. So what do we actually want to do? We want to negate this intrinsic disadvantage of gallium oxide. The problem is that if you want to make a device with this material with such poor thermal conductivity, this may cause significant damage to the device from overheating. So can we negate this, mitigate these disadvantages by attaching gallium oxide to a suitable high thermal conductivity substrate? The obvious endgame applicant for this would be diamond with around 2000 watts per meter per Kelvin thermal conductivity, but silicon carbide or sapphire would also work in the meantime. So we want to know if we can adhere gallium oxide to a high thermal conductivity substrate. What would be the electronic and thermal properties of that new structure, and what useful devices can we produce that way? So what do we actually want to achieve? Ideally, we want to have a large area gallium oxide with good addition to the chosen substrate in a way that is reliable and reproducible. We want to have an option for the thickness of the gallium oxide layer. A very thin layer would actually be very useful for carrying out XPS measurements, so for band alignment with the substrate, and larger ones from few tens to 100 nanometers would also be good for electrical as well as thermal characterization. Okay, so now let's talk about the method. The method using liquid gallium droplets takes advantage of some of the particularities of metallic gallium. So first of all, it has a very low melting point, just above room temperature, 28 degrees. So it is easy to turn into liquid state. It also easily oxidizes in air. So a passivation layer is formed naturally on the surface of any liquid gallium, which is a few nanometers thick and covers the pure gallium core. So it doesn't passivate to a large extent within the droplet, but just on the surface. So the main idea of the deposition would be to heat up some gallium onto a hot plate. We used 50 degrees Celsius. Grab a droplet with a pipette and touch that in some way to a substrate. For initial calculations, we've used silicon with silicon oxide thermal layer, and then this thin layer of gallium oxide that is formed on the outer surface of the gallium drop will be in contact with the substrate and be attached with van der Waals forces to it. Some caveats, however. In order for this to work properly, the substrate needs to be treated with oxygen plasma. This makes the surface hydrophobic and more likely to adhere to the oxide. The other thing is that naturally there will be some excess gallium that will have transferred with the gallium oxide onto our substrate. For this, the actual sample is afterwards cleaned, and the excess gallium is brushed off in heated methanol. This method has kind of been adapted from a few papers who have done similar things with gallium oxide. So here is some result from this. You can see a large magnification of the gallium oxide film onto silicon oxide, and some AFM that shows these film thickness between 5 and 10 nanometers. Later work also showed that the same deposition method can work on diamond. So yeah, this has been a success as far as the deposition is concerned. So I think the most important question to ask really is this really gallium oxide that we've actually transferred? And this is not really an easy question to answer. I've looked at some data that kind of looks at thin layer epitaxial growth of gallium oxide onto aluminum oxide and gallium oxide and the XPS data of that. And you can kind of see that there are some vague differences between the spectrum of the gallium metal, the gallium oxide, and well, the whatever the paper's epitaxial growth was. Mostly, I want to draw your attention to the secondary small hump just over 20 electron volt binding energy on the bottom, which is the XPS data from one of my samples, which is prominent in the sample for the reference sample for beta gallium oxide from that paper, and not prominent in the gallium metal. Of course, this is not enough. I want to talk a bit more about this. You can also see this, the data for the primary gallium peaks. You can certainly see that there is a certain splitting in most of the samples shown, which indicates different levels of oxidization of the gallium, which is not present in our sample. So this means we have we have a single level of oxidization throughout the film. Of course, this can be seen both in the cases of metallic gallium and of gallium oxide. However, it can be definitely seen that the value of the binding energy peaks does increase with oxidization. And I haven't put it here because space, but these peaks have shifted from the peaks that have been taken from the bare silicon oxide XPS, which can only show some gallium traces that have survived post-cleaning. So now onto the band alignment measurements. I've kind of taken reference from a paper that did a band alignment of beta gallium oxide to silicon. I think they sputtered it or something. So what we need to do is use the relative valence band positions taken from the UPS for the thin film and the bare stuff, the core levels, the silicon 2p and the gallium 2p binding energies from the XPS. And with this formula on the top, we can pretty much get what the valence band offset at the interface would be. Yeah, just a bit of a talk of how the data was manipulated. These are some examples of the silicon 2p peaks. The upper one is on the gallium film. You can see some of the gallium peaks as well. The data was fitted with Gaussian fitting to find the position of the peaks. As for the UPS and the valence, a linear fit was put onto the rising slope of the spectrum to get a consistent value for both measurements of the silicon substrate and the gallium oxide thin film. And as a result, the knowing that the valence band offset between gallium oxide and silicon oxide was estimated as 0.45 eV. If we take into account that the silicon oxide to silicon valence band offset is 4.36 electron volts, that would if we imagine them gallium oxide to silicon, and we squish the silicon oxide, the gallium oxide to silicon valence band offset with these calculations would be 3.9 electron volts, which is close to the reported in that paper 3.5. Of course, I don't actually have values for the band gaps of these as of yet. I've just used the literature values for this demonstration. So now that this initial measurements are done and the deposition is seen to be a success, there's a few things that need to be done in the future. First of all, this current deposition should be amorphous, taking into account the metastability of beta gallium oxide. Annealing should be done on these samples to create a polycrystalline film rather than an amorphous. Band alignment calculations should be also done for the diamond substrates or any other substrates of interest, and also for the polycrystalline film variants after the annealing. Thermal characterization should be also carried out, and depositing contacts for measuring electronic responsive samples. Thank you. Any questions?
I don't know how we're going to clap. Thanks, Alex, for a nice talk. I'm monitoring the chat. Has anybody got any questions? If so, please type them into the chat. Let me start with a question then. So, Alex, you mentioned that it will be an amorphous film that grows on the surface of this droplet, and you have to anneal it. So what are the criteria for making a good gate dielectric? Is it sufficient if it's just polycrystalline, or does it has to be pinhole free, obviously? So how strict are the criteria?
I'm not actually sure on this. I know that, so the thing is that with the amorphous deposition, you don't really know what the what kind of gallium oxide you have. So we want to anneal it just to make sure that we have it in the beta phase that we know. Does that make sense?
Yeah, okay, all right. Dan Wolverson, I think, has a question. Dan, do you want to unmute?
Yeah, so my question, I might have missed it because my internet collapsed for a moment, but have you looked at Raman in these materials? Because beta gallium oxide has a very interesting Raman spectrum, a lot of peaks, and it's very characteristic for the material.
Yes, yes. The issue with the Raman is that I don't think we can characterize this with Raman, because whilst it's really interesting, the Raman's signal from the gallium oxide is really weak, and it's almost almost impossible to distinguish the peaks from noise if it's under like 100 nanometers.
Yeah, I'd be very interested to try with UV Raman. So we have a 5 eV photon energy in our Raman microscope, which is close to resonance with the GA203 band gap, which it might work. So it might give us a bit more signal strength. we can talk about this separately, but
Yeah, yeah.
interested to try that. Yeah.
That's interesting, yeah.
Okay, great. I don't see any more questions in the chat line, so let's thank Alex again. I don't know how we're doing it. Clap or raise a hand. Thanks, Alex. So our next talk is from Ben Smith from the University of Bath. Ben, are you ready?
Yes.
Great. Okay.
Can you see my screen?
Yep. If you want to go into presentation mode, then we're ready to go. So Ben's talk is photoemission studies of the charge density wave material tantalum sulfur selenide. All yours, Ben.
Great. Thanks for tuning in today, everyone. So as Simon just said, I'm going to be talking about photoemission studies of the charge density wave material tantalum sulfur selenide. Just do a few quick acknowledgements. I'd like to thank my supervisors in Bath, Dan Wolfson and Enrico Tacomo, a lot of students who have worked on this study in Bath, Matia and Gary at the NanoESC facility in Bristol, the beamline scientists at Spectro Microscopy, and the funders at EPSEC and CDT-CMP. So to give a bit of a historical background to the key physical effect that we're going to be looking at today, Einstein won the Nobel Prize in 1921 for his discovery of the law of the photoelectric effect. And the photoelectric effect, as I'm sure we all know, is the emission of electrons from a surface when light is incident upon it. And Einstein fleshed out the theory of this effect, and one of the key equations he derived is that the maximum kinetic energy of the photoelectrons is equal to the energy of the incoming packets of light minus the work function of the surface. So XPS is a technique which is built upon this photoelectric effect. So XPS stands for X-ray photoelectron spectroscopy. And in this case, our light source are monochromatic X-rays, which are directed at our sample. Electrons from the different core levels of the sample's atoms are emitted with different kinetic energies corresponding to their binding energies within the atom. So in XPS, as I say, we measure the kinetic energy of the emitted photoelectrons. We fix the photon energy, and we can fairly easily find the work function in the material, which then allows us to fairly easily calculate the binding energies of the core levels, and we end up with a quite a characteristic spectrum for different materials where we've got a number of peaks with different binding energies. So now I'll just talk about charge density waves, which are a feature of the material that we're looking at. So if we just consider a one-dimensional chain of atoms where the atoms are spaced periodically with periodicity A, and that's in the normal phase. And then if we go to the charge density wave, what happens is that there's a distortion of the lattice to form pairs of atoms or dimers of atoms. And this lattice distortion leads to a modulation in the density of electronic charge. So we now go to this black curve on the right where the density of electron charge is modulated. With this lattice distortion, there's a reconstruction of the lattice to a superlattice with new periodicity. So we've gone from periodicity A to periodicity 2A in the CDW phase. And if we look at the electronic band structure, we can see on the right that a gap opens at the Fermi level and the occupied bands are lowered in energy. And we'll generally see a CDW transition occurring if the energy that's gained by lowering the occupied bands is greater than the energy cost of distorting the lattice. So the material that we're looking at is a member of the transition metal dichalcogenide family. these materials have the chemical formula MX2, where M is a transition metal atom and X is a chalcogen atom, so one of sulfur, selenium, or tellurium. A single TMD layer consists of an X-MX sandwich, and within a layer there are strong covalent bonds between the atoms. But between layers, there are only weak van der Waals interactions. And because of these weak interlayer interactions, it's quite easy to remove layer by layer by exfoliation, right down to a few or even single layers. There are lots of different compounds in the TMD family, showing lots of different properties and phases. So we see metals, semiconductors, semi-metals, etc. And we often find that the properties change drastically as a function of the number of layers. So a classic example is molybdenum disulfide, where in the bulk, in its bulk form, it's an indirect bandgap semiconductor. But when we reach the monolayer limit, we find that it becomes a direct bandgap semiconductor. So the specific TMD we're looking at is an alloy, tantalum sulfur selenium with 1.2 parts sulfur. And the tantalum-based TMDs show lots of, well, they exist in lots of different polytypes and display lots of different CDW phases. And that's shown in the table on the right for the 1T polytypes. And in both cases, at low temperature, we see a CDW phase with root 13, where it's a root 13 commensurate CDW. This CDW phase is shown on the bottom left. So we see we've got this lattice distortion to form a new superlattice, which is known as a Star of David superlattice in this case. And within this superlattice, there are 13 atoms with 3 different inequivalent sites. So there are 6 atoms on the tips of the star, 6 atoms on the ring, and 1 atom in the center. So this material was grown in Bath by Charles Sayers and Enrico Di Como using the chemical vapor transport method. And they were grown in their bulk form. I don't have any images of this specific alloy, but there's some images here of other 1T TMDs, which generally look quite similar. And this that I'm about to show you is XPS data collected at the spectrum microscopy beamline at Electra, and we acquired XPS measurements on 2 full cooling and heating cycles. And at the bottom, I've shown quite a broad spectrum showing lots of the different peaks from the different core levels of this material. So we've got selenium 3D peaks, tantalum 5P peaks, and most interesting for us, the tantalum 4F peaks. So if we look at these peaks in a bit more detail, we see that there's 2 sets of peaks separated by spin orbit splitting. And then for each of these sets of peaks, there is further splitting, which is induced by the CDW phase transition. And the reason why we see this extra splitting in the CDW phase is because of that superlattice that I showed you earlier with the inequivalent atomic sites. So essentially, one of the peaks arises from the 6 atoms on the ring. The other peak arises from the 6 atoms on the tips. And in theory, there should be a third peak from the single atom in the center, but this will have much lower intensity and is probably hidden under the other peaks. And this splitting is known to be a good indicator of the CDW strength. So if we look at these tantalum 4F peaks as a function of temperature, the key result we see is that there is more splitting at lower temperature, which is telling us that there's an increasing CDW amplitude at lower temperatures. So as I mentioned, we acquired these XPS spectra on 2 full cooling and heating cycles. between 300 and 100 Kelvin. And again, you can see that at lower temperatures, we generally see more splitting, but also interestingly, there's quite a strong dependence on the heating and cooling cycle that we're on. So for example, at 200 Kelvin, we see quite different splitting depending on the heating or cooling cycle. So for example, between the black and the blue data points. So there's some quite interesting hysteresis effects going on here. If we then look at some resistivity measurements that were collected by Liam on the same material, we again see some quite interesting dependence, not only on temperature, but also on the heating and cooling cycle. So again, for example, at 200 Kelvin between the black and the blue curve, there's quite different resistivities. And then very briefly, we've got some temperature-dependent Raman measurements, which were collected in Bath. And this is just for one heating and cooling cycle. And again, we see evidence of these hysteresis effects. And in this case, the Raman temperature dependence matches quite closely to the resistivity temperature dependence. So to summarize, this material was grown in Bath and characterized using XPS resistivity and Raman. And for each of these techniques, we saw quite interesting hysteresis effects, which we'll need to try and disentangle with future measurements. Thank you all for listening. Any questions?
Thanks, Ben. Let's have a look at the chat. Nothing yet. Okay, can I ask a quick question? So
Yeah.
at the lowest temperatures there, you have a state where the resistivity differs by orders of magnitude.
Yeah.
The XPS splitting actually looks almost the same for that part on the hysteresis cycle. Is that easy to understand?
I've gone back. So, yeah, it's not easy to understand because we're seeing quite different hysteresis effects depending on the technique. We could be seeing more resistivity because of potentially a MOT phase, not just a CDW phase. The XPS splitting is only telling us about a CDW, but if we've got other interesting effects such as a MOT transition going on, then that could affect the resistivity without showing in the XPS.
Yeah, sure. Okay, we have questions. We have a question from Phil King. Phil, do you want to unmute?
Hi, yeah, thanks very much for the nice talk. If I remember correctly, at least some of these compounds have both incommensurate and commensurate CW phases.
Yeah.
Does this one show that? And if so, do you see any evidence for this in the XPS results as well?
Yeah, so I know that the pure compounds have incommensurate phases at higher temperatures. We didn't really see any evidence for incommensurate phases. I think normally you wouldn't see any splitting at all because you need the CDW to be coherent over quite a long range. So I think the fact that we're seeing quite strong splitting tells us that this is a commensurate phase at all the temperatures we're looking at.
Great, thanks very much.
No worries.
Okay, we have another question from Chris Bell. Chris?
Hi, Ben. So yeah, about the hysteresis again, I mean the width. So first question, just generally, why is it so broad? And then second question related, if you go to the next slide where you had the resistivity and the Raman, yeah. So I guess they're quite similar, but actually the Raman is much broader.
Yeah.
If this breadth is associated with disorder, for example, so you've got different patches, I could imagine that, say, the Raman or the spectroscopy or the resistivity are quite different because, resistivity, you're averaging everything, whereas Raman, you're focused down. So I just wondered what your thoughts were, just generically, about the width.
What do you mean by the width exactly?
Why is the hysteresis so wide in temperature?
I don't really know, to be honest. I mean,
compared to other related compounds, is it much bigger, much smaller?
So this is quite an interesting So this alloy in particular has been known about for quite a long time, right back to the 80s. And they looked at lots of different alloys with different compositions of sulfur and selenium. And for this particular composition, they saw these very interesting hysteresis effects, for 2 full heating and cooling cycles. For these materials in general, you will see some hysteresis on the resistivity. But for this one, the effects are really a lot more complicated. And I don't think, I'm not fully sure exactly why at the moment. So we've got some RPES measurements as well, which will maybe tell us a bit more about what's going on. But yeah, we're not fully sure yet.
Yeah, that's fine. It's a work in progress, no problem.
Yeah.
Thank you.
Yeah, this is clearly a very complex material. Okay, I think we'd better move on. So let's thank Ben again quickly.
Cheers.
Thanks, Ben. And the last talk in this session is from Sabrina Waters. Sabrina, are you there? She has a joint affiliation Bristol and Bath. Sabrina.
I'm just going to share my screen.
Okay.
Accidentally minimized it.
Okay, so assuming you haven't changed the title, this will be Electrochemical Studies of the Deposition of Platinum Nanostructures on Gold Substrates via Surface Limited Redox Replacement.
Yeah, so that's the title of my research, and as Simon's already said, my work was carried out in both labs in both Bath and Bristol University. So the motivation of my research primarily focuses on the potential applications of the 2D arrays of platinum nanostructures, which we hope to achieve. These applications include catalysts, sensors, and electrical applications like transistors. This method suggested in this talk also offers a relatively cheap, simple method of producing homogeneous arrays of 2D platinum nanostructures. In order to do this, we use a lipid structure as a template, and so far as I know, this has not been explored before, but it would offer an easy design of uniquely small structures that can't be achieved by any other methods. The advantage of an array of platinum nanostructures is the benefit of control, so we can control the area and the spacing between the subsequent particles. With control of these parameters will come a better understanding of the density and the platinum coverage, and also to look at the high control of the surface reactions. So the overview of my project can be explained in this simple schematic. So the aim is to use a template consisting of a self-assembled lipid cubic phase. The lipid will be transferred onto a flat gold substrate via a templated method. In this research, we've been considering spin coating as an appropriate method. Electrochemistry will then be optimized to deposit the platinum in the holes of the template and onto the gold substrates via a method called surface limited redox replacement. Removing the lipid template should reveal a 2D array of platinum nanoparticles on the surface of the gold. So the basis of this research can be split into 2 groups for now. Overall, we want to form the lipid cubic phases on the gold substrates to deposit platinum in them. The first one, we need to look at the lipid cubic phases. Initial experiments included changing the ratio of the lipid by adding in a swelling agent. This would tell us if there was any changes in the cubic phase to the diameter of the water channels, which we get. Then studies were done on the thickness of the lipid layer using ellipsometry, followed by studies on the diffusion of the reaction carried out using the standard redox reaction of ferricyanide. This would help provide some information on how and if the lipid changes the diffusion of the species. This would help build a picture in order to see the effect the lipid has on the processes at the surface of the gold in order to optimize the lipid template for the platinum deposition. The second area of this research focuses on the electrochemistry on the gold substrates. So preparations of gold substrates by annealing and characterization of copper UPD processes were observed, followed by optimization of the surface limited redox replacement method. Finally, bringing both areas together to hopefully deposit the platinum using the lipid template and get the 2D array of platinum nanostructures we want to achieve. So first of all, a bit of background about lipids. So the lipid used in this project is phytontrol. So phytontrol has a hydrophilic head and a hydrophobic tail, and on the left we can see the phase diagram for phytontrol. When phytontrol is placed in some composition of aqueous solution around room temperature, the molecule will self-assemble into a cubic phase. There are 3 lipid cubic phases which can be formed: primitive, diamond, and dioroid. The one that we're considering is diamond. So this is when you place phytontrol at room temperature around 30 to 35% of composition of water. So the diameter of the water channels in the cubic phase can be altered. This is done by adding in a swelling agent. In our case, we're using Breed 56. The Breed 56 molecule penetrates through to the phytochar bilayer, reducing the negative curvature of the diamond cubic phase. This leads to a flattening of the bilayer curvature, increasing hydration and widening the diameter of the water channels. This is a very important factor in our research, as the water channels are the holes in the template whereby we will deposit the platinum later on. The tunable diameters of the water channels mean we can achieve a range of nanoparticles of various size, which may have different potential applications. A small angle X-ray scattering was used to analyze the lipid cubic phases formed in initial experiments. So the Anton Parr SAX instrument was used to bombard the sample with X-rays. And some of the incoming X-rays are scattered at the sample interface by elastic scattering, and some are transmitted through. The X-rays are collected onto the 2D plane detector, producing an interference pattern, which can be converted to 1D, as seen here on the right. The 1D diffraction pattern obtained has a unique set of Bragg peaks. Using the equations on the left and the information from the 1D SAX plot, the lattice constant of the cubic phase can be determined. For phytocontrol in excess water at room temperature, the lattice constant is around 6.8 nanometers. Knowing this, we can then go on to calculate the diameter of the water channels. The other primary experiment studied on the lipid cubic phase was the standard redox reaction of ferricyanide. Ferrocyanide may be oxidized to ferricyanide. This is a reversible reaction. Using the information extracted from the cyclic autogram provided and the equation below, the diffusion coefficient D of the reaction can be obtained. All electrical chemical measurements were performed in the 3-electrode cell as seen here. The working electrode is the sample we are investigating. The counter electrode is primarily a platinum wire, and the reference electrode either a saturated calomel electrode or a silver-silver chloride. And the electrolyte in the cell changes depending on the electrochemical experiment performed. The electrochemical methods for the platinum deposition in this study utilizes a phenomenon called under-potential deposition. Under-potential deposition, or UPD, is the formation of a metal monolayer on a foreign metal substrate. This process occurs at potential less negative than the potential required for bulk electrodeposition. This research focuses on platinum deposition via a copper UPD monolayer. Whilst there's been a lot of interest in forming platinum layers on gold substrates using a lead UPD layer, this is the first time the concept of using a copper layer in a sulfate solution in a one-cell configuration has been explored. The method used for depositing the platinum on the gold substrate is called surface-limited redox replacement. So SLLR is the formation of an atomic monolayer of a sacrificial metal, which is then galvanically replaced by a more noble metal. This can be explained when we look at typical platinum deposition transient on gold substrate. In the first few seconds of the scan, the copper ions in the solution begin to form a copper UPD monolayer on the gold substrate. At step 2, we can see that as the open circuit increases with time, the platinum ions in the solution begin to replace the copper atoms one by one, until at step 3, the copper atoms have all been replaced and we have a full monolayer of platinum on the surface of the gold. This process can be repeated until the number of layers you require is reached. So on to some results. So these were early results. These were of confined lipid cubic phases of various ratios of phytocontrol and swelling agent, constructed within thin polyimide tubes, filled with Aquarius solution and sealed with heat shrink tubing, as you can see on the left. SAX was performed on each sample, and these are some of the results. So these studies were carried out in order to gain proof that we determined the diamond cubic phase formed between phytocontrol and water, and also to see the effect of the swelling agent. So the graph on the left shows the 1D SAX plot of some of these samples. Each result has 6 distinct Bragg peaks, which corresponds well to the diamond lipid cubic phase. The plot on the right originates from the relationship between the Miller indices and the distance between the planes, and the gradient of the line of best fit to this plot is equal to the lattice constant of the cubic phase. From these results, for 100% phytocontrol, the lattice constant was determined as 6.8 plus or minus 0.2 nanometers, the same as that found in literature. As the content of Breed 56 is increased from 0 to 20%, the lattice constant increases from 6.6 to 12.7, which is as we expected due to the widening of the water channels, and hence the lattice constant increasing. Our results conclude that we've successfully attained the diamond lipid cubic phase with a tunable water channel diameter. The redox reaction of ferrocyanide was performed on a gold substrate and on a lipid templated gold substrate at various scan speeds, and the results can be seen here on the left in the CVs. The CV for the gold with no lipid template shows a nice reversible reaction with an obvious anodic and cathodic peak. As the scan rate is increased, the distance between the minimum cathodic and the maximum anodic current density remains the same, indicating a reversible reaction. From a plot of the maximum anodic current density versus the square root of the scan rate, we see a strong positive correlation where a linear line of best fit fits well, and the gradient of this line can be used to determine the fusion coefficient, which came out as 10 to the minus 5 centimeters squared per second, corresponding to the value found in literature. When the same experiment was repeated on a lipid templated gold, the results can be seen to dramatically change. We no longer observe nice anodic and cathodic peaks at certain voltages. Instead, we observe plateaus of currents or current density. The lower the scan rate, the tendency towards plateauing current is more obvious. One possible reason for this is due to channel diffusion. What we seem to observe in the CV is consistent with that of a steady state reaction. One possible reason for the steady state profile is the idea that the current reaches the bulk value when it reaches the gold substrate. Preliminary results of the ferrocyanide redox reaction on lipid templated gold poses a diffusion coefficient much smaller than that on normal or on bare gold. This is expected due to the complexity of the water channels. Steady state profile observed also suggests that maybe a slightly different set of equations may be needed to determine the diffusion coefficient, as the linear relationship between the square root of scan rate and maximum current density no longer holds. More tests need to be done on this to fully understand what's happening at the surface and in the template. Elipsometry experiments were also performed to determine the thickness of the lipid. The results showed that if we spin coat in a one-step process, thickness of the lipid increases linearly with 1 over the square root of the spin speed. But as these results were done on lipid spin coated onto silicon, not gold, we need to change the model on the ellipsometer in order to see if this still holds for a different substrate. Moving on to the second area of the research. So I've been looking into optimizing the electrochemical processes on bare gold substrates, so without the lipid template. This is so I can build up a picture of what happens in each reaction at the surface, so that I can make the correct changes for the process for the lipid experiments in order to achieve the results we want. So first I did some investigations into annealing. Samples were flash annealed with a butene torch for 20 seconds. On this graph here, we see the gold oxidation cyclic voltagram of 3 samples. The gold oxidation was done in 0.1 mole of sulfuric acid at 50 millivolts per second, and the 3 samples were taken from the same gold slide. 20 seconds of annealing the surface of gold produces a similar CV through all 3 samples with little variation. We see this as the gold oxidation peak, and the cycle around the potential looks the same for each set. So 20 seconds of annealing seems long enough to improve the surface of the gold in all 3 samples, and we have a presence of the gold 111 peak on the CV, indicating a good surface. The nice sharp reduction peak also allows us to calculate the electrochemical active surface area. Then I carried out platinum deposition via the copper UPD process using SLLR on 3 samples, depositing 2 layers, 5 layers, and 10 layers of platinum. The transients follow the trend of a typical deposition onto a substrate using the SLLR method. The copper is deposited in the first 3 seconds and then begins to be galvanically replaced by the platinum. The 2R transients seem to take longer to deposit in the first and second layers than the 5 and 10 layer. The hydrogen UPD was carried out on 3 samples after deposition, and the CVs can be used to determine the platinum roughness. The hydrogen UPD cyclic voltagram should be similar for repeating repetitive results, but this wasn't always true. We thought this may be due to platinum clusters on the gold could be contaminated with copper during the SLR replacements. However, XPS measurements showed that less than 3% copper was present on the surface of the gold after platinum deposition, which means there's no significant contamination coming from the copper. So one of the other reasons for this may be due to an unstable environment in the system. So there's a worry that there may be depletion of chloride ions in the bulk of the system. So when the copper forms the UPD monolayer on the surface of the gold substrate, platinum ions in the electrolyte begin to galvanically replace the copper ions one by one. And as the platinum does this, it breaks apart from the platinum chloride molecule. Therefore, we have the assumption that there is an imbalance of chloride ions in the system, with a surplus amount near the working electrode and a deficiency in the bulk of the system. With this, it means that we could have an unstable environment, meaning the deposition of the platinum analysed by the hydrogen UPD may not always be the same each time. Also, as the number of replacements has increased, the percentage of chloride ions also increased near the working electrode, making an even more unstable environment. So in order to account for this, I added 10 to the minus 6 molar sodium chloride to my electrolyte and repeated the experiments. We can see the hydrogen UBD curve here seems more stable, with the 2, 5 and 10 replacements more evenly spaced if we look at the left-hand side. The transients again seem more compatible, with the time taken for the first 2 suppositions very similar for all 3. So in the next few months, we'll focus on the study of the diffusion of the species with respect to the lipid layer. So this will include using Cottrell's equation and Fick's law to analyse the data and determine new diffusion coefficients. I also start to work on a detailed study of the effective thickness by changing the spin speed at which we coat the sample, or the concentration, and see how this might affect diffusion as well. I also want to repeat the SLR platinum depositions with the addition of extra chloride to see if this is repeatable and is true that we do have a deficiency. Optimization of the electrical chemical processes on bare gold will be thoroughly studied in order that we can repeat it on lipid templated gold. We'll also be looking into AFM and XPS in order to characterize the surface of the deposited platinum on the gold and lipid templated gold. So this will be so that we can observe the shape and size of nanoparticles produced and also the composition of the elements on the surface. So in conclusion, the next few months should bring with it the progress on the electrochemistry so that we can transfer the work from the bare gold substrates onto lipid templated gold substrates. Thank you for listening. Any questions?
Sabrina, nice talk. Let's have a look. Kei, I think Kei Takashina has a question.
Hi, thank you very much for a very nice talk. You showed a comparison between the cyclic voltammograms you get from a bare electrode and one covered with a template. I was wondering, for the templated version, have you tried experiments with the bridge in which the channel diameters should be different, and so you'd expect things like diffusion to be different if they're limited by things like the tortuosity or the geometry of the water channels?
This one, sorry, this slide.
Yeah.
Sorry.
Have you tried the experiment with bridge?
Yes, and so with different ratios of bridge, you still get the plateauing of currents.
But do you get more current, and how does it scale with the expected changes in the lattice constant and things like that?
So I've only tried with small ratios of bridge, so like 5% and 10%, and there wasn't a lot of difference compared to the ones without bridge. So I think I need to increase the percentage to maybe add 20% bridge and see if that makes any significant difference.
Right. Okay, thank you.
Okay. I don't see any more questions in the chat, and we're actually slightly over time. So let's thank Sabrina again for the talk and everybody else in this session. So it looks like we have a short break now. We will resume at 11:20. I'll see you all then.
Okay, so it's time to start the next session, and I can see Tobias there ready to give his talk. Each year we have a speaker from industry or from a facility, and this year we have Tobias Lindstrom, and he's going to tell us about life in the National Physical Laboratory, where he's been working on superconducting quantum technology. So can you share your screen now, Tobias?
Hopefully, can you see my screen now? I started sharing.
We can see you.
Okay, can't see my screen.
I can see your screen.
Oh yes, sorry.
Okay, great. All right, so I'll start then. Yeah, so good morning, everyone. And I'd like to start by thanking the organizers for inviting me. So as mentioned, I'm Tobias Lindstrom. I work at the National Physical Laboratory. And I believe my role in this conference is to sort of represent industry. So I'm actually going to split my talk into 2 parts. I'm going to start by talking a bit about NPL and what we do, and maybe a bit about what it's like to work there. And then there's going to be a part 2, which is going to be on microscopic tool-level systems and the role they play in superconducting quantum processors. And the second topic I picked because there's a connection to condensed matter. But it's also, I think, a very good example of how sort of fairly fundamental research that started at NPL about 10 years ago or so has now developed into something we're actually using with, when we're working with partners in both in academia and industry. So let's start from the beginning. So what's NPL? Well, the National Physical Laboratory is the UK's National Measurement Institute, or NMI. So we are located in Teddington in southwest London, although we have a couple of regional hubs. At any given time, there are between sort of 750 and 1,000 people on site. We're fully owned by the government. We operate as a company, but we're owned by the government, and we also part funded by the government, although we also do sort of commercial work. And we are about, on site, we're about 400 different laboratories. So on the left there, you can see our main building, and then on the right, our brand new advanced quantum metrology laboratory, which hopefully will be ready for us to move in, later in the spring. So what do we do? So NPL's main mission is, this slightly grandiose text that says, provide the measurement capability that underpins the UK's prosperity and quality of life. So many people, believe that the P in NPL stands for physics, which it does not. It stands for physical. And we actually cover not just physics and engineering. We cover quite a large, large number of topics. Pardon me. So anything from electromagnetics, temperature, biometrology. We've done actually quite a lot of work on the COVID research. We do data science and so on. So the bit I belong to is quantum technology. So I'm in the Department of Quantum Technology, specifically in the group on quantum information processing. So, okay, so we cover a lot of topics, but what is it that we actually do? Well, the core activity of NPL, or the core mission, I should say, is that we maintain and disseminate the SI. So most famously, that means that we keep track of the UK time. So we are the ones who have the atomic clocks to send out the time signal. However, it's not just enough for us to maintain the SI, we also develop it. So we do a large amount of, in terms of research, a lot of that is related to improving the way we sort of realize, that means how we actually implement the SI. So as hopefully many of you know, the SI was completely redesigned last year, and that was in part thanks to research done at NPL. So how you actually implement the system unit and how to improve them is an important part of the research we do. But separately, well, somewhat separately, part of our mission is also to act as a bridge between academia and industry. So, for example, we can have something that's developed in an academic group can do instead of come to NPL, some idea or a new instrument or something, and then be a bit further developed before it's transferred into industry. We also help companies specific measurement problems. So that will typically be companies trying to develop a new product or trying to sell something, but they run into an issue because they need to measure something really accurately, and they don't maybe have the expertise or the facilities for doing so. So then they will come to us, and we'll hopefully be able to help them with that. We also provide measurement services, and again, this is a bit of a misconception because a lot of people think that's the only thing we do. It's not. It's maybe 1/4, 1/3 of what we do, and this just basically means that let's say a manufacturer of instrumentation needs to have a very accurate resistance standard or in their own lab. So they will then take that, drop it off at NPL, ask us, can you please calibrate that against your primary standard, really good primary standard, and then we'll send it back to them. But last but not least, and this is probably the bit the part of the work I do is more on the sort of fundamental research. And this is usually in collaboration with universities. And it is, can be, on topics, it's a bit difficult to describe, but basically what we try to do is find topics which might be relevant to us in the future. And I know that's quite vague, but what it basically means that if we see that in maybe 10 years' time, we think there's a pretty good likelihood that a company will knock on our door and say, look, I have this measurement problem. Can you help me calibrate this? Or can you help me solve this problem? If we think that's going to happen in 10 years, that means that we actually have to start working on that now. So we have to develop the expertise and the facilities on more widely the capabilities for doing that. So the most famous example, a good example of that, I should say, would be quantum technologies, because 10 years ago most of these were in their infants and it was more sort of seen as sort of blue sky research. But today we're of course seeing an emerging industry, and we literally have companies knocking on the door now wanting to do, say, quantum computing. Now I know this is sort of, in theory I should be sort of advertising and say MPLL was great to work at, and I think it is, but it's perhaps not for everyone. So I think it's a good place to work at if you like work on applied problems. So if you prefer to do sort of pure curiosity-driven research where, with no sort of known application, well, MPL is probably not for you, because the type of research you do, even when it's fundamental, typically should lead to some form of application in the end, or at least have the potential for an application. Most people at MPL also end up at least working in part with industry. That depends, of course, what area you're working on. So me personally, 5 years ago, I didn't work with industry at all. But again, this has now changed. So now suddenly I'm working quite a bit with different companies. So you need to like the idea of having some sort of working with industry and working with commercial partners. So again, if you're already, a perfect job is to work in a sort of purely academic environment, and you, for example, you like to teach, MPL is probably not for you. And then last but not least, as I said, MPL is quite a large organization. There's about, nearly 1,000 people on site. And this is pros and cons depending on who you are. I mean, the pros is that, that means that you have the opportunity to move into different areas if you want to, and you can sort of move horizontally. But then there are, of course, many people who just like to work in a small organization or company. So, it depends on who you are and what you'll prefer. Now, let's say you're hired by MPL. One thing I should say, that one major difference between working as a scientist at MPL and, let's say, a university, is that nearly all positions at MPL are permanent. So we don't really have, say, postdoc positions. People are typically hired with permanent contracts. So if you come to MPL and apply for a job and you have like a master's degree or equivalent, you will typically join us as a high research scientist. Whereas someone, who already has a PhD, will then join as a high research scientist. And then, of course, there's a ladder. Your career progress, and you get promoted to ultimately to an MPL fellow if you're lucky. And as you progress, and this is obviously similar to most other organizations, as you progress, you'll be expected to take on more responsibility for managing projects and people. I should say, again, as I mentioned, it is possible to move horizontally. So, getting promoted is not the only way to sort of change your roles. You can also move to another team who might need your specific, area of expertise, even though they work on a very different topic. All right, so I'm coming towards the end of part one of my talk, but I should, of course, advertise that we are actually, the Department of Quantum Technology, which I belong to, is hiring at the moment. So we have a large number of vacancies out. So if you're interested, you can either sort of write down this link, or maybe just sort of Google MPL and careers, and you'll find it on our careers page. So the current deadline for applications is the end of this month. So let me move to part two, and this is the two-level systems that I talked about earlier. So as I mentioned, we do a lot of fundamental research, and I think this is, hoping that this might one day lead to, have applications. And this is, I think, is a very nice example of that. So, and it has to do with measurements of intrinsic noise superconducting quantum circuits. Now, if you look at the photo on the right here, you'll see something that's probably quite similar to what you would see in a press release from, say, IBM or Google or something, right? And this is a quantum computer, but it's not the quantum computer. It's a dilution refrigerator. So it's just the fridge. It's just the cooling system, right? If you want to show something that more represents what's actually in a quantum computer, this is probably a better photo. So this is one of our samples. This is this photo shows a qubit, which is at the bottom, which is this plus or this cross, which at the bottom, which if you squint, you might be able to see, will have two Josephson junctions, and that forms what's known as a transmon qubit. And then you see this meandering line above that, which is a quarter wavelength resonator. So the quarter wavelengths and the qubit together are sort of the core elements of any superconducting quantum computer. Now, these layers are typically made from aluminium, niobium, or some other superconductor, and then obviously in between these layers you then put a dielectric, which typically is aluminum oxide, And then these are patterns similar to what you do in, say, CMOS into Josephson junctions for the qubits, resonators, and other circuit elements. It's very important that the processes are fabricated on substrates that have very low loss tangents, very low loss at microwave frequencies. So typically you use sapphire or maybe high resistivity silicon. So loss tangents is sort of ordered, sort of low 10 to minus 6. And as mentioned earlier, these systems are operated in dilution refrigerators, so they're bolted to the bottom of what I showed you on the photo earlier. So they typically operate at a temperature below sort of 50 millikelvin, and in many cases even much lower than that. Now, what a lot of people don't realize when talking about quantum computers is that some of the main obstacles for scaling up quantum computing, to the point where they're sort of practically, useful in real life, is actual material science. So it turns out that many, or at least some of the defects, impurities, including paramagnetic spins, that you would just find naturally in these materials, in these metals, in these dielectrics, tend to behave as two-level systems when you cool them out to millikelvin temperatures. And by two-level system here, I mean literally like a textbook quantum mechanics two-level system. So similar to what I show on the photo below here. So these are really, they're not that many of them because the materials are clean. So typically you find that the most problematic two-level systems in terms of surface is about sort of 1 per square micron, which again is not much, but it's enough to sort of mess up the qubit performance quite a bit. And there's also in the background a sort of a spin density, some paramagnetic spins that for fairly universally is about of the order of 10 to 17 per square meters. So importantly is that, well, I should say one reason why this is such a problem is that we don't actually understand what these two-level systems are. We have some ideas and we have identified some of them, but there's a lot of stuff that's unknown about them, which means it's very, very hard to get rid of them, and that's what we want to do. Because what they cause a lot of issues, both in terms both in terms of energy relaxation, dephasing the qubits themselves, and also parameter fluctuations. I'll show you that a bit later. So, as I said, already said, we don't actually know what these are, and I'm not going to go into this picture in detail, but just to show you some of the possible mechanisms that people have been discussing for a number of years. You have anything from mid-gap states to bistable structures, adsorbates on the surface, which by incidentally is something we've done the work on at MPL, etc. So there's you can probably find 10 other suggestions for exactly what these two-level systems are and which ones, where people are trying to pin down the ones that are most problematic. So I should also say that just earlier this year, we at MPL added yet another mechanism that could maybe work as an TLS to this zoo. And then we would show that this could also be due to trapped quasar particles on the surface of the superconducting films. So, okay, so I've told you about this TLS, I told there's a problem. So how do you actually notice them? Why do they show up? Well, if you just take a superconducting resonator, just a bit of what I showed you earlier, just this meandering line here, which is a quarter wave resonator, and you measure its resonance frequency, you'll, we're using like a network analyzer, so you'll get this curve, and you have a resonance frequency at, in this case, sort of 5.15 gigahertz. But if you actually zoom into this and you look at the frequency as a function of time, what you actually see is this is going on. So the frequency is actually sort of jittering, it's moving back and forth. And let me remind you that this is a sample that can sit at 10 millikelvin, so you think that everything is going to be quiet, but it's not. There's a lot of noise going on there, and this noise is intrinsic, and it has to do with the material. And you have, you have different types of noise, but again, so we can identify, but that's a bit of another story. They're all related. Most of this noise is related to these two-level systems. Now, if you then add a qubit at the bottom of this resonator, there's another problem that crops up, and that is not only are these two-level systems causing problems in terms of the coherence of the qubit, but also cause what's known as parameter fluctuations. So if you actually just measure the qubit, in this case, the relaxation time for the T1 over and over again, over a long time, this time over 60 hours, you see that varies quite dramatically. So, and this is obviously an issue, right? If you want to run an algorithm on your quantum computer, and then it takes, let's say it takes an hour to run, and then 20 minutes into your calculation, suddenly something happens and the T1 of all the qubit drops, or maybe just one of the qubit drops, then your algorithm will fail. So, this is a serious issue. And this is actually one of the main limitations with existing sort of quantum computers that you can access via the cloud, these parameter fluctuations. So we got interested in these problems about, again, 10, 12 years ago. So when we started, playing around with superconducting resonators, because we did realize that superconducting quantum computing was going to come along, and it's going to become important. And being a measurement institute, we thought, okay, maybe we'll have a go at looking at this noise. So one thing we realized that in order to do this properly, and I should say, we were not the first people to look at the noise, but we wanted to do it quantitatively and do it well. It's actually not trivial. You can't just do it with a network analyzer. So because we realized we needed to be able to resolve changes of the order like 1 Hertz for 6 gigahertz resonator. So that's of the order 1 part on 10 to 10. Now, working at an NMI, what we did was we just walked over to our colleagues to do frequency metrology and asked them for some advice. And what they suggested was that we should look at what's known as a pan loop technique. And if anyone listening now has done work with stabilized lasers, they will recognize this, because that's how you stabilize, that's how that's done as well. So we took this basic idea, and I'm not going to explain how this works, but it's basically a feedback technique. And we adapted that so that it could be implemented around at low temperatures and so on. So this turned out to be an extremely powerful technique, because what it allows us to do is actually get the time series. So we can get these the resonance frequency of the resonator as a function of time, and this time can be up to many, many days if we want. And once we have that, we can then use a battery of standard techniques from frequency metrology, Allen deviation, FFT, cross correlations, etc., to look at the noise in more detail. So, and when we did that, we actually realized, if you do this properly, you can then start modeling that. So we then started, collaborated with some theory groups. And because we had done this, really well, and we had really good measurement data, we could work up some new models for what was going on, and we learned quite a lot about these two-level systems. And I'm just showing you a graph here, and again, I can't go into details because of lack of time. But what I wanted to highlight is that these points here are just amplitude of 1 over f noise, the intrinsic 1 over f noise, as a function of the number of the energy being pumped into the resonator at different temperatures. So one curious thing here, which is a bit counterintuitive, but we do understand thanks to this model, is that the noise actually goes up as we reduce the temperatures. So the noise is lower at 500 millik than in the 13 millik. And it turns out this has to do with the fact that these two-level systems are not independent, they actually interact. So this was sort of a new twist to what fairly old field, which is known as glass physics. Which, we actually learned quite a lot of new fundamental physics thanks to these measurements. And again, I don't have time to go into details of how this model works or what we think is happening on the surface. But the point here is that thanks to these accurate measurements and the fact, we were able to develop this model. And today we're now using this model to extract material parameters, so TLS density, intrinsic loss time, etc., etc. And we can do this by measuring the frequency noise of a fairly simple resonator using this pan loop. And this has turned out to be an efficient way to extract material parameters that are relevant for quantum computing. And this is now something we actually use when we work with partners, including companies. So I'm going to stop there, and I'm going to ask if anyone has some questions. Thank you.
Okay, sorry, I'm just getting control of my. I can see there's a question from Chris Bell. Chris.
Hi there, and thanks for the nice talk. I just had a quick question about, so if I think of this as a spin glass, this collection of paramagnetic spins, this is probably a bit of a stupid question, but what happens if you apply a big magnetic field and spin split these levels or do something like that? Obviously there's impact on the superconductor, but just as a thought experiment in the first instance, what would happen?
The answer is not very much. So one thing I didn't have time to mention is that one thing we can actually do, because with this, since we have this resonator, we can actually, if we apply a magnetic field, we can actually use this for ESR. So we can actually use this to map out the spectra. So this ESR combined with the noise measurements is actually quite a powerful tool. But what we've shown is that, yes, we are splitting these levels and so on and in the spins, but it doesn't actually affect the noise level directly. We do know that if we anneal the samples and we desorb some of these spins, the noise actually goes down quite a bit. But again, you have to keep in mind, as I said, there are lots of different two-level systems here. So we don't think the spin glass, they are in the background. I mean, even though that some of this is hydrogen sitting on, at least on sapphire, this is a hydrogen sitting on the surface that's absorbed on the surface. But some of the more problematic two-level systems, which is this density 1 per square micron I mentioned, is probably not hydrogen or any sort of spin glass or anything like that. So we think what's happening is this interaction is affecting this. So we have this problematic two-level systems, which might in theory be very stable and you sit there, but because you have this large population of spins around that, they are sort of kicking this two-level system in the middle. That changes its level splitting, which means it's sort of jumping around in the frequency spectra, and then occasionally it will come into resonance with your qubit, and then the qubit will slowly decohere. So when I showed that it's varying T1, what we think is happening is that we have a fairly small number of strongly interacting two-level system, meaning they're strongly coupled to the qubit, but there's a huge spin, relatively speaking, huge spin population around them, and this is sort of moving around, and these spins have energies that are probably lower than sort of the 10 millicale or whatever you're sitting, so they can still move. And then just because they move around, then you occasionally they'll kick this two-level, the strongly coupled two-level system that moves, and then the qubit is affected. So this is why these interactions are so important for the model. And if you neglect interactions, nothing really makes sense. And that wasn't obvious when we started this work.
Okay, great, thank you.
Can I ask a question, which is, you said you didn't know what the two-level systems actually were physically, I think?
Yes.
I mean, so does that mean you don't know which elements? You mentioned hydrogen there, but could there be impurities that you could find?
People have tried. The challenge you have is that as far as we are aware, there are no standard methods for analyzing surfaces that work because the densities are actually too low. So I mean, we talked to a lot of people who do surface analysis, do SIMS, for example. But it's actually quite difficult, if you have, let's say for sake of argument, you have one two-level system per square micron. There's a huge background, and it's actually very difficult to pinpoint it. So people have tried to figure out exactly if it's, it's like a foreign element, but no one's had much luck. It's also quite unlikely that this is as simple as an ion sitting there, for example, because you would then be able to affect it. You would apply a magnetic field and you would Zeeman split the levels or something like that, and that's not the case. So it's probably some sort of tunneling effect. So something that can be in two states and tunnel between them. And then they're in the position where this potential that they're sitting in can be changed by the spins, for example, in the around them, so that the spins are affecting the potential of some object, whatever it is, that can tunnel between two different states. But yeah, no. So the short answer is there is no sort of clear-cut answer. There are lots of candidates, as I said, but no one knows what it is, and unfortunately, it's unlikely to be just BFA for an impurity, because this is seen in a huge number of materials as well.
Okay. Daniel Wolverson had a question, I think.
Yeah, I already posted it on the chat. I thought it was very interesting that you corrected some misapprehensions about what MPL does. I wondered on that subject whether there are opportunities for computational and theoretical physicists at MPL too. I'm sure that there are.
The short answer is yes. So we do, even in the we have a so Ivan Runger in the QIP group, so the Group group I belong to. He's doing a lot of sort of DFT calculations and stuff like that. Although these days he's actually done quite a lot of work on quantum software. So basically doing sort of materials science and materials calculations, the DFT type calculations on quantum computers.
Right.
So although it's true that the majority of people who work at MPL are experimentalists, we do have a few people who do theory as well. Not as many, but yeah, there are certainly opportunities like that.
Yeah, thank you.
I think Kia has a question.
Hey, yeah, can I ask a... Yes, please. I was wondering about these impurities that's causing decoherence. Superconducting qubits are very, very big. And I was wondering where in the device are these, and wondering are there particular bits of it that you want to keep clean, and whether or not there are prospects for having architectures or designs so that we avoid them.
So it's a very good question, but which unfortunately I could give you a very long answer. I think the short answer is we believe the majority of them are at interfaces, and most likely that's the interface. Most of them are actually at the interface with the vacuum. So if you that could be so let's say you pattern a structure, right? You will have the superconducting film itself will probably they'll probably have some oxide on there. And then we believe that there are two-level systems sitting in that sort of surface layer. You can also have two-level systems sitting just directly on the surface of the substrate, and that's for the hydrogen, adsorbed hydrogen I mentioned earlier. It's actually not sitting on the superconducting bit; it's sitting on the substrate. But that's close to since that's close to the qubit, it still has an effect. So we don't think so. I think the shortest answer I can give is we think these are mainly located at various interfaces and not in the bulk. But that's basically as far as we can get. You can, we have done work as well. We're trying to pinpoint them, and you can, do some clever experiments. But basically, all you can narrow it down to is yes, it's probably at the surface somewhere, and most likely. It has something to do with the something on the let's say the oxide on the superconductor surface, or adsorbents on the substrate surface. I can give I'm happy to give a much longer answer offline if you're interested.
I was just wondering if it was particularly sensitive at the junctions and things like that, but by the sounds of things, no.
So it's I think if you go back sort of 10 years, there were a lot of people worried a lot about two-level systems sitting inside the junctions themselves, so inside the aluminum oxide layer.
Yeah.
Partly because the junctions these days are much smaller, and partly because we're tend to be a bit better at fabricating them. That's rarely a problem these days. So it's probably not going to be inside the junction. But yeah, of course, it's true that if you have something sitting next to the junction, so let's say you might make your sandwich, for example, and then just next to the junction, let's say 100 nanometers away, you have a strong two-level system. It will be a problem. But more generally, it has to do with where the electric field is strong. So it can even in a transmon, even in the big capacitor, which is huge, right?
Yeah.
Even there, you can occasionally see that you can couple to an individual two-level system. And that's experiments we have done at NPL. So you have this huge structure. You can still see one TLS, which is in itself quite fascinating.
Okay, thank you.
Okay, thank you for that. I just so I think that's all the time we have for the questions. I'd like to thank Tobias again for giving us a very nice talk about what life is like in MPL and some of the exciting research that's been going on there. So,
thank you.
That's from me. Thank you very much. Let's move on to the next talk, which will be from Liam Farah.
Yep, can you hear me okay?
We can.
Cool, let me just. Cool, and is that coming up okay?
Yep, so Liam's going to tell us about Josephson phenomena in van der Waals heterostructures. So off you go.
Cool, thank you very much. My name's Liam. I'm a fourth year CDT student, if no one knows me. And today I'm going to be discussing Josephson phenomena in van der Waals heterostructures. So first of all, I'd like to break this down to two parts. So what is the Josephson phenomena and what are van der Waals structures? And then hopefully my talk is going to tie them in together to explain what you can do with those two concepts. So we start with the Josephson phenomena. If we take two superconductors, A and B, and they're connected via a weak link C, so this could be like an insulating barrier, then classically these two materials are disconnected. However, quantum mechanically, we know that electrons can tunnel between the barrier if it's sufficiently thin. Under no applied voltage, there should be no tunneling. However, Cooper pairs can tunnel between the superconductors via the Josephson effect. So these weak links can be created in a variety of ways, such as thin insulating layers, non-superconducting material, so a SNS junction, or physical constrictions, a variety of effects. And these are highly important in uses such as superconducting quantum electronics, as we saw in the previous talk. So these can be used in things such as squids, magnetometers, and NMR machines. They're used for all sorts of things in metrology, geophysics, even things such as gravitational wave detection. And nowadays, there's a lot more push towards using superconducting qubits, where Josephson junctions are one of the main components. And so next, what's the van der Waals side of this? Well, if we go back to 2004, the Vozilov and Geim first isolated graphene. So they took graphite, which consists of individual layers of this graphene, which is a 2D material, so it has these strong in-plane covalent bonds where it's got this weak outer plane dispersion, so you can rip apart the layers. And they ripped apart this graphite into a single layer and showed that it had this nice electric field effect. And this started the 2D revolution. So where did heterostructures come into this? Well, a few years later, in 2010, a group decided to use boron nitride. So this is a wide bandgap insulator, and they actually managed to stack their graphene on top of the boron nitride to make the first, at least that I know of, heterostructure. So what else can you do? Well, there's not just this graphene material and boron nitride. There's a whole host of families of 2D materials, all the way from insulators, magnetic materials, all the way to superconductors. And here's just a list from a commercial supplier. And there's 20 different superconductors you can buy in bulk form, and in labs across the world, there's many more. So how do we combine this Josephson phenomena and these van der Waals heterostructures together? Well, luckily, we weren't the first ones to do this. So back in 2016, a group based in Japan actually decided to stack two nibin diselenide, which is a superconductor with a TC of about 7K, and it's one of these van der Waals materials. So they took two layers and they stacked them together. They measured the IV curve across the junction in between, and they showed some basically some Josephson phenomena. So they saw this retrapping current, and in a magnetic field, they could suppress the critical current here, which is what comes from these Fraunhofer-like patterns from the Josephson junction. If they look at the interface, they did some TEM, and they saw that when they stack these together, it's a planar junction. So the flakes themselves don't curl down the sides, and the connection is just from the top to bottom. And from this, we wanted to look at a few effects. So mainly, what causes this weak link? As here, there's no insulating layer. There's just two superconductors stacked on top of each other. Is this effect just related to nibin diselenide? Can we do this in any other materials? Is there any twist dependence on the junction behavior? So here in the bottom, there's a Fermi surface of nibin diselenide. If you twist these layers, does that cause any effect? And the main thing I'm going to talk about in this presentation is, can you make more complex superconducting devices? So we start with how do we make ours? So we use a very similar method to the Japanese group. So if you start with this exfoliated flake from a bulk crystal, you just use sticky tape and you put it on some polymer, which we call PDMS. You then align using a microscope setup this over some gold contacts on SiO2, and by simply bringing the PDMS with the flake into contact with the surface, the flake likes to stick to the nice, clean, flat silicon dioxide. And here on the right is just a few microscope images of this happening. And again, we're looking for this planar junction effect. So you can not only stack one flake, you can stack multiple. So this is our first junction. The two flakes here, and again, nibin diselenide, the different color just comes from the fact that they're different thicknesses. If we cool the flakes down, we measure the resistance versus temperature, we can see that the flake in blue, we measure one of them has a sharp DC about the same value as bulk. And if we measure the junction, although it's got a slightly lower RR, so it's got some increased scattering at the interface, it is still superconducting at the exact same temperature. So we know we've made at least a good superconducting connection between these two flakes. If we then measure IV curves, we can see the presence of this supercurrent region. And if we look near 1 millivolt, we can see very nonlinear IV curves. This indicates that there's some intrinsic effects here. And if we measure the DI/dV, so we do numerical derivative, we can then look and we can see some quite interesting peaks. So if we compare our DI/dV to the previous group's results, here in the bottom right, what they saw were very sharp peaks as a function of temperature, and these don't look like what we see here. Instead, what we're looking at is a measurement of the density of states at the Fermi level, and this is indicative that instead of a Joseon type junction, like the previous group saw, we're more towards the tunneling junction end, where we can measure the density of states. So why is this, and why are our results different? Well, this was just our first sample, so we decided to measure a few more. And here we can see if we twist these junctions as a function of angle, we can pick up quite different effects, going from a underdamped junction with these distinct retrapping currents all the way through to these reversible junctions, which show these quasi-particle gap structures. And I won't talk about this in too much detail, but I will talk about this over lunch at my poster. So see that if you want any more details. So instead, what we're looking at is a more complex device, and one of these is a superconducting quantum interference device. So what is this? Well, if we look back to our Joseon junction, Cooper pairs are coherent, so we can compare a Joseon junction to, say, photons in a laser beam. And here the analogy combining these is that the magnetic field is our quantized photon and the junction is a single slit. So what happens if we put this in a magnetic field? Well, we can use the field to modulate the Joseon phase across this junction. And in some parts of the junction, the supercurrent flow must be opposite, and this results in interference, or the classic single slit Fraunhofer diffraction pattern shown here in the bottom left. Now, what happens if we combine two of them together? Well, if a Joseon junction is a single slit and a squid is a loop consisting of two Joseon junctions, then the analogy here is that this is a double slit or a two-slit diffraction pattern. So if we consider a loop with no Joseon junction, the phase must be the same at the start and end, so there must be a 2π difference. When a magnetic field is applied to the loop such that flux passes through it, there's going to be an additional phase shift. Now, if we add the second junction, the phase must be the same at the start and the end, and the phase difference is phi1 and phi2 across the junction, and because of this, they're in a loop, they're not independent, and so phi1 and phi2 equal this equation in the bottom right. Now, the sum of the supercurrents is going to be the same. Then we can see as we apply magnetic field, we're going to tune the flux through this junction, and we can oscillate the critical current. So here we get this interference pattern, and not just the Fraunhofer from the single junction. These are mainly used in magnetometers, and they're typically made, as we've seen in previous talks, of niobium or aluminium with an oxide layer in between. However, we want to make these out of our Van der Waals devices. So how do we do this? Well, if we take our Joseon junction, and what we can do is just mill 3 holes in. So one on the two on the sides to shape the junction, and one in the middle to separate the Joseon junction itself into 2 individual ones. So we just do this using reactive ion etching, and in the bottom left, this is a junction which just has these holes milled through, and the dark regions here are the 2 Joseon junctions forming the squid loop. Here, if we measure the IV curves, we can look at the characteristics of this. So here we just use a copper coil with a small field through, and we can apply them up to microtesla. And the area of the junction itself, the loop itself even, dictates the field required to oscillate the current. So here we apply at the maximum value of critical current and the minimum, and this is something between 50 and 100 microtesla, and we can see we can oscillate the critical current quite nicely. If we then, say, apply a constant bias and measure the current as a function of magnetic field, we can recover these interference patterns, so this nice oscillation of the critical current. Here, if we look at 700 millivolt bias, we can see a modulation depth. So this is the difference from maximum to minimum critical current of about 30–40%. And if we go all the way to 90 millivolts, we can see up to 75% modulation depth. Here, there's a bit of noise, and this is just due to the fact we're using a closed cycle cryostat. So there's some refrigeration cycle, which is causing thermal fluctuations and introduces a bit of noise into the system. The good thing about these is that the modulation depth is large compared to commercial squids, where the change it from maximum to minimum critical current might be a few percent. Here, we can change it up to all the way up to 75%. And part of the interest here is by changing the angle, we can look at non-hysteretic junctions, which we can then use in what's called a fixed current mode. So here we can apply a constant current and then measure the voltage. And by doing this, we can also recover oscillations in voltage with a change in voltage of 1.4 millivolts, which is very large compared to commercial junctions. So from this, what we've done is managed to create a quite high quality squid. So next, we can think about, okay, are there any other 2D superconductors we can use? We might think about putting different materials in the spacer layer. So rather than just niobium diselenide and niobium diselenide, we might use a ferromagnetic or anti-ferromagnetic material in between. And we have done this. I won't talk about this in too much detail, but we've managed to make junctions from niobium disulfide and niobium disulfide on top of my niobium diselenide. And with that, I'd like to thank my collaborators, especially my supervisor, Simon Bending, and I'm open to any questions.
Okay, thank you very much, Liam, for a really nice talk. I haven't got any questions yet, but maybe can I ask a question? Does this type of squid have advantages over other squids? You seem to be implying that the sort of parameters were larger than other squids. So
yeah, so I just had a quick look on, say, Google to see what squids you can buy, and comparing, say, the voltage difference. So if you want to make a low noise squid, you need a large voltage modulation because the amplifier electronics can induce a lot of noise. So I haven't looked at noise measurements, but at least from this seems like they can make very high quality low noise squids. I think one of the good aspects of this is a single crystal, so rather than a film. And I think part of the interesting aspect is the fact that you could make these out of a variety of materials. So this kind of opens up a new type of device where you might think about putting, say, like a topological insulator in here and seeing what might come out.
Okay, Tobias Lindstrom has a question.
Yeah, I was just wondering about if the material properties of the niobium selenide is well known. Is that just a sort of a pure S-wave BCS superconductor, or is there anything more exotic going on?
So it's, yeah, it looks like it's a anisotropic or two-gap S-wave system. It's basically, we had a very high quality crystal, but we have looked at other devices. So one of the things we were looking at is iron selenide, which is a interesting unconventional superconductor. You can also make something out of bisco, say. This can be used for any variety of materials. So you can make a high TC bisco device using the same technique.
Okay, good. Well, that's all the time we have for questions. So thank you again, Liam, and
thank you very much.
Let's move on to the next talk. So Oliver's going to tell us about the impact of impurities on the spin Hall effect in beta tungsten.
Hi all. So I'm going to talk about the impact of impurities in beta tungsten. This is my first publication. It just got published last week. And before I start, I'd like to thank my collaborators, Dr. Martin Gradhand, my supervisor, and Dr. Derek Stewart from Western Digital. And also I'd like to thank Wenfeng Go from the Western Digital Summer Internship Program for providing some calculations. And also I'd like to thank the CDT, the EP, SRC, and Western Digital for funding and allowing me to do this project. Okay, so first of all, let me give a little background into what the spin Hall effect is. So if you look at the figure on the right, if you have a non-magnetic material and you have a charge current, JC, then you will end up having a transverse spin current, JS, due to the spin Hall effect. So this is the simplest picture. So the red arrows are upspins, the blue arrows are downspins, and you get this separation in the material. So you can define the spin current as the difference between the upspin and the downspin in a given direction, whereas the charge current is the sum of these two things. From this, you can derive a figure of merit, the spin Hall angle. So the spin Hall angle is defined as the ratio between the spin current and the charge current. And this is also the ratio of the spin conductivity in the direction of the spin current and the charge conductivity in the direction of the charge current. So the spin Hall angle is going to be an important metric that we're going to talk about. So Western Digital are interested in using this in memory applications. Okay, so the material I've chosen is beta tungsten. There's a couple of reasons. I'm just going to go through why we've chosen this material. So you want ideally a high spin Hall angle, which means you get lots of spin current from the charge current that you put in. So materials with large spin Hall angles tend to have high spin orbit coupling and high resistivity. So spin Hall angles scale with both these things. So if you look at the table here, you can see the resistivity of the beta phase of tungsten, which is in the A15 crystal phase, compared to the common BCC alpha phase of tungsten. And you can see the resistivity is a factor of 10 higher. And as you can see, the spin Hall angle has been measured to be much higher in beta tungsten compared to alpha tungsten. Platinum is another common spin Hall metal, but that still has a much smaller spin Hall angle than beta tungsten. However, beta tungsten doesn't exist in a pure form. It requires oxygen or nitrogen impurities, for example, to stabilize it. So because of this, we aren't sure of the exact mechanism that is causing the spin Hall angle. So we're going to talk a bit about the intrinsic and extrinsic effects within the spin Hall effect. And so the purpose of this research is to ask the question whether it's intrinsic or extrinsic effects that are important in beta tungsten. So the mechanisms, first we'll talk about the intrinsic effect. So the intrinsic spin Hall effect is the spin Hall effect that is caused from the spin orbit interaction, and it arises from the geometrical properties of the crystal. If you look here, this is the band structure of beta tungsten. The red dashed lines refer to the band structure without spin orbit coupling turned on, and the black solid lines are with spin orbit coupling turned on. So we've calculated these, and as you can see in the blue circles, you have gaps appearing over the Fermi level, and here you have some spin orbit splitting. So these things lead to a very large intrinsic, one of the causes for a large intrinsic spin Hall effect. Now the extrinsic effect is different. Oh, sorry. And it entirely depends on the impurities within your sample. So up electrons and down electrons will get scattered in different directions because of impurities. So when we're looking at these two effects, we need to use two different methodologies to examine both the intrinsic and extrinsic effect. So for the intrinsic calculations, for the electronic structure calculations, we use quantum espresso, and then to find out the transport properties of the material, we use PAO flow. And all the calculations there are in reciprocal space. However, for the extrinsic, you need to do a slightly different method. We use the screen KKR method, and the reason we use that is because quantum espresso doesn't allow you to take into account scattering from impurities. So this is the method we need to use. And we use a real space impurity solver to create a Green's function, which gives us all of the transport information, which we can solve with the Boltzmann equation. So my first set of results. So here we have the intrinsic spin Hall effect in alpha tungsten and beta tungsten. So if you look at the conductivities, on the magnitude of the spin Hall conductivity that we've calculated, you can see that beta tungsten has a much higher spin Hall angle. So we calculate between 20 and 55% here than alpha tungsten. And this is the spin Hall angle due to intrinsic effects only. So this agrees pretty well with the literature. But the problem is, in real life, you don't have a pure beta tungsten system. You have to include the effects of impurities. So whilst this spin Hall angle is in pretty good agreement, yes, impurities are important. And the reason the range is so large is because the range in resistivities is large. So it depends on your measured resistivity, what spin Hall angle you get. Intrinsic results. So we then used quantum espresso to calculate spin Hall conductivity in doped systems, but this is again just the intrinsic effect. So there's no scattering effects in these calculations. And you can see that for doped systems, both oxygen and nitrogen, that the spin Hall conductivity, the intrinsic spin Hall conductivity, is suppressed, which is unusual. But it might be that extrinsic spin Hall conductivity is high in these doped systems, and that's the reason it appears lower than the experimentally measured systems. So for extrinsic calculations, we look at all the different impurity sites, which I'm highlighting here on the right. So this is your beta tungsten unit cell. And we look at each of these sites individually and average them out. So the extrinsic calculation, as I said before, takes into account scattering from these impurity sites. But what we find is that for beta tungsten, the intrinsic spin Hall effect is entirely negligible, giving only a spin Hall angle of 0.06 for the extrinsic part, which is much smaller than for the intrinsic. So this is also surprising. So to summarize the results in this table, you see for beta tungsten, for the pure system, you have a large intrinsic. For the doped systems, you have a slightly smaller, well, half the size in the intrinsic, and the extrinsic is very negligibly small compared to the intrinsic effects. So that this is strange because we would expect this number to be larger. So we need to consider what assumptions we've been making throughout the calculations. So in these calculations, in these intrinsic calculations, should I say, we assume that the impurities are spread pretty evenly throughout the beta tungsten structure. But what we think might actually be happening is that the impurities themselves are migrating to the grain boundaries between the beta tungsten grains, leaving pristine beta tungsten, and therefore increasing. So therefore, when you measure it experimentally, what you're actually seeing is the intrinsic pristine beta tungsten, and the impurities migrating to the grain boundaries may actually increase the resistivity and also enhance the spin Hall conductivity. So we believe this to be the best explanation for what we're seeing, as it's clear that extrinsic effects aren't relevant and the intrinsic effect is suppressed if you assume an even distribution of impurities. So yeah, in conclusion, intrinsic effects are important pristine calculations agree with good with experiments, whereas dope calculations do not. And we believe that impurities are migrating to grain boundaries to explain this. Thanks for listening. Any questions?
Okay, thank you very much, Oliver. So I have a question for you, which is, why does beta tungsten have such a high spin Hall effect? Can you relate that to the Fermi surface? Some special
you can actually relate it to the Fermi surface. I was going to include, we did some Fermi surface calculations in the study. I was going to include them in the PowerPoint, but we didn't because of time constraints. But what you see when you look at the Fermi surface is that areas on the Fermi surface with high Berry curvature, which is linked to the intrinsic spin Hall effect, don't mix with areas on the Fermi surface that have high spin mixing. So because of that, yeah, you get a really large intrinsic effect because if the Berry curvature is high in the area where there's not much spin mixing, yeah, then the intrinsic effects will be enhanced because you have more of one up or down, if that makes sense.
Yeah, okay. Simon Bending has a question.
Yeah, thanks, Oliver. You mentioned at the beginning that the company was interested in memory applications for the spin Hall effect. I was just curious what sort of structures they were investigating.
The main structure we're interested in is something called spin orbit torque MRAM. So for spin orbit torque MRAM, you have a spin Hall metal, such as beta tungsten, and you have a small magnetoresistive tunneling layer with a ferromagnet. And the idea is if you create a large enough spin current, then you can actually flip the magnetization of the ferromagnet and create a bit. And you don't require any external fields for this. It's a non-volatile memory. And just to reverse the bit, you just pass a current in the opposite direction. So that's the kind of device we're looking towards.
Okay, thank you.
Okay, that's it on the questions. So thank you again. Let's move on to the next section.
Thank you, everyone.
It's going to be the lightning talks, something we've not attempted before online. And I'm going to hand over to Tom, our centre manager, to do that.
Hi, everyone. I'm just going to post a message in the group chat. Just put a list of the talks there. So these are all the people that are giving posters. And we've added Liam. He's going to do a poster and a lightning talk as well. And so, yeah, this it's going to be fairly rapid fire. 1 minute. 1 minute per person, starting with Amy. I'm going to be just timing it with my phone. I'll give you a 10-second warning maybe. And then when your minute's up, if you haven't stopped speaking, I might mute you and move us on to the next one. Are you ready, Amy?
Yeah, I was told it was 30 seconds, so I might just speak really slow, but okay.
Garrett is, I might have got that wrong. I think we've got enough time for a minute. Are we going to should we go for a minute?
I can embellish, yeah. Okay, no problem.
Well, yeah, I mean, if you're between 30 seconds and a minute maximum.
Okay, cool.
Yeah, okay, so time starts now, yeah. If you go.
Hi, I'm Amy. I've got a poster today detailing how I made a strontium titanate-based electric double layer field effect transistor and how it's been successfully fabricated such that an ohmic contact has been established with the surface 2-deg and a metal to insulator transition is seen. I discuss why it's interesting to gate this material in this way using an ionic liquid as opposed to a solid dielectric like silicon dioxide. I detail the steps that are necessary to make these type of field effect transistors. And then I go on to sort of talk about what we can investigate now that we've got a working device using things like Raman or electronic transport. So yeah, thank you. Come and see my poster.
Okay, great. Thank you. So next up, we've got Charlie Hall. Charlie, are you ready to go?
I'm ready if you can hear me.
Yep, can hear you. Okay, go.
Okay, so hi, I'm Charlie. I'm working at the University of Bristol in the chemistry department under the supervision of Dr. Simon Hall, no relation. So in our group, we work with organic crystals, the most common, well-known of which are pharmaceuticals. So we're looking at the creation of new crystal structures using a variety of techniques to improve the efficacy of these pharmaceuticals. So in my poster, I'm talking about a method using deep eutectic solvents or volatile deep eutectic solvents for this. Sorry, I managed to get called during this. Sorry about that.
Sorry, you still got 10 seconds.
Okay, deep eutectic solvents, volatile ones to make new crystal structures, and we showed that we can make a metastable form 2 paracetamol crystal, which has higher efficacy than the first one, easily at room temperature. Come see my poster for more info.
Thanks. Okay, next up we've got Joe Hitchin. Joe, are you ready to go?
Yeah, sure.
Okay, go.
Okay, my work's basically looking at charge transfer systems, so that's co-crystallizing organic compounds. The main thing I'm looking at the moment are compounds based on the electron acceptor TCNQ, which is an aromatic ring with 4 cyano groups on them, which is a very strong electron acceptor. I'm taking the pharmaceutical paracetamol, but I'm actually using the ortho position. So the ortho position of paracetamol, I'm co-crystallizing these two things together to create a charge transfer complex. I'm characterizing these things by UV, IR, and DSC to see whether we can transform these into new compounds. And additionally, I'm also looking at changing the orthocetamol to paracetamol and metacetamol and seeing how that modifies crystal, the unit cell. I see you waving your hands.
Yeah, that's it. Yeah, your minute's pretty much up.
Okay.
Thank you. Okay, next up we've got Lawrence Gammon. Lawrence, are you ready to speak for a minute? Okay, off you go.
Okay, hello everyone. My poster today is about a project my group in Bath has recently been working on in collaboration with groups in Germany and Brazil. The material we're studying has potential for use in battery applications, and producing them via the glass ceramic route can enhance the conductivity, whilst giving the advantage of moldable bulk materials. So to gain insight into this process, we've been investigating the glass structure and how it changes upon crystallization. So looking into whether we simply see an ordering of the glass network or a reorganization of structural units. And I thought it was 30 seconds, so I'm done there.
Done. Okay,
Yeah.
That's very good. Thank you. Next speaker is Will Luckin. Will, are you ready to give us your 1-minute pitch?
Indeed so.
Go.
So, I'm Will Luckin. I've been working at the University of Bath with Dr. Martin Michałkuczyński. And has this ever happened to you? You've been sitting there at home during lockdown, happily modeling a transition metal dichalcogenide with a tight binding model, and you just find that there are too many orbitals. Well, if so, weep no more, because we've got the solution. We've made an effective model of tantalum diselenide with only 2 orbitals per unit cell. We showed that that's a valid description by calculating the spectral weight and showing that these 2 orbitals contribute most of the spectral weight for the bands around the Fermi energy. And then using our effective model, we made predictions that characterize the charge density wave state and compared those to ARPES data. If you want to know more, come and look at my poster.
Thank you. Next up, we've got Jared. Ready, Jared?
Yeah.
Okay, go.
Cool. So my poster today is going to be looking at the uranium oxides. Our interest in them is kind of atypical, rather than looking at them as like a nuclear fuel problem or power generation. We're interested in trying to make semiconductor devices using these materials. And they've been shown to have a wide range of promising properties, but it's not fully understood due to the changing and fluctuating oxygen stoichiometry seen within these systems. So today we're going to be presenting a fabrication route to obtaining single crystals of the uranium oxides and trying to gain some understanding into their structure. So yeah, come along.
Thanks, Jared. Next up, we've got Lucas. Are you ready, Lucas?
Yeah, I think so. Can you see me?
Oh, okay, off you go. Thanks.
Hello, my name's Lucas, and my poster today is about using optical methods to measure chirality. We call objects chiral if the mirror images cannot be superimposed on the original objects. And despite chirality being very widespread and having important applications and in pharmaceuticals, for example, the methods to measure chirality have not really changed for the past 100 years. We've been looking at measuring chirality through nonlinear light scattering. And in my poster, I show that we're able to distinguish between two chiral versions of nanoparticles, even if we measure a single nanoparticle at a time. If you would like to learn more, please come have a look at my poster. Thank you.
Great. Thank you. Next lightning talk is Chloe. You ready, Chloe?
Yeah, I'm ready. Hi, everybody. So I'm Chloe, and my poster is titled Phonon-Induced Optical Dephasing in Single Photons from Organic Molecules. So I'm looking at a particular molecule called DBT, which has some quantum information applications that I'm going to go through in my talk. And on the poster, I'm going to detail an open quantum systems model, which can effectively capture the emission spectra from these molecules, and it looks up in detail as how to characterize the various different phonon dephasing processes. And then after looking at all of the different kind of aspects in the emission spectra, I'm going to then use that to show some new results on the indistinguishability of these molecules, which haven't yet been characterized by experimentalists. And I'm looking at for the case where they're filtered and then also put into a microcavity, and that is everything. Thank you.
Thanks, Chloe. Next up, finally, we've got Liam. You ready, Liam?
Yep. So I'm just going to chat a bit more about my presentation from earlier, mainly focusing rather on the squid stuff, but on the angle dependence of these junctions. So yeah, come along if you want to talk about that.
Great, thank you. So that concludes our lightning talks and pictures of the posters. And so the poster session will, be just after lunch, 1:15. Stephen, should I hand back to you to just wrap up this session?
No. Well, thank you all of you for your contributions. So just to remind you, this poster session will be from 1:15 till 2 o'clock. And when you come back, you'll see that we'll set up some rooms for you to go into. So everything should be clear what you have to do when you come back after your lunch. So, but please could you just leave yourself logged on, muted, and turn your video off while you're having lunch, so Tom can change the status of people so that they'll be able to move around in the poster room. Okay, thank you. So see you later.
So welcome back to this session. It's a great pleasure to be able to ask our second invited speaker, Professor Phil King from the University of St Andrews, to give us his presentation. And the title of this is going to be Spin Orbit Coupling, Correlations and Inversion Symmetry Breaking. Phil.
Great, well, thank you very much for the introduction, and it's really very nice to be virtually here with you all at your first online conference for this. So I want to tell you today about some work that we've been doing, which sort of tries to look at the intersection of where we have a decent strength of spin-orbit coupling, a relevant strength of electronic correlations, and we put this all in an environment where you can maximize some of these effects. And for us, this is going to be in a broken inversion symmetry environment. Sorry, I'm slightly losing my voice, so if you stop being able to hear me, just yell out. Please also feel free to interrupt me as we go through the talk to ask questions as we go. I'm very happy to take them as we go along. Okay, so the most important thing I should do is point out the people that really led the work, and you can see them on the slides here. So actually, both of them were graduate students that were joint between my group and Andy Mackenzie's group at the Max Planck Institute for Chemical Physics of Solids in Dresden. And so these were both really exceptional students. Veronika Sunko is now a group leader in Dresden, and Igor Markovic is staying with us for a postdoc at the moment. And they led the projects that I'll talk to you about on delaphocytes and on rutheniates, respectively. And so this whole thing has been a nice collaboration, actually, between our group in St Andrews and Dresden. And we did various measurements at different synchrotrons along the way, at Diamond in the UK, at Elettra in Italy, and at MaxLab in Sweden, in the days when we were still able to travel between all these countries to do these synchrotron measurements. Okay, so I guess if we look back at condensed matter physics over the last few years, there've really been, well, a number of very important themes, but I would say two of the strongest have been the physics of strong correlations and the physics of spin-orbit coupling. And so in strongly correlated electron systems, we know that the strong interactions between the electrons and between the electrons and the crystal lattice and so on lead to an entangling of the behavior of these electrons together. And perhaps one of the most profound consequences of this are the very rich phase diagrams that we find in these systems. So as you change some tuning parameter, and this could be carrier doping, this could be pressure, this could be magnetic field, you find that the system tips between many different ordered phases. And I guess maybe one of the most famous examples of that these days is that of the high temperature superconductors, which you see here, where you move from Mott insulating states, antiferromagnetic ordering, superconducting states, and then these kind of enigmatic pseudogap and strange metal states. On the other hand, I think we've seen in the last decade or so a real resurgence in interest in spin-orbit coupling in solids. Now, we've known about spin-orbit for a long time, of course, but for a long time it was treated as something of relatively minor significance, at least in solid-state physics, and just, you know, a relativistic correction that we didn't really need to think about in most cases. And at least over the last decade or so, I think we've really seen that rewritten. The most famous example probably being the discovery of topologically non-trivial phases of matter, and in particular where spin-orbit driven band inversions between your valence and conduction bands in the solid can give rise to new states where you have to have these gapless spin polarized Dirac surface states at the surface of your material. And so I guess many of us have been interested in both sides of this, in strong correlated physics and in the physics of strong spin-orbit coupling. But there's typically been a bit of a disconnect between these two areas. And the reason for this is really rather simple, that if you want to have strong spin-orbit coupling in solids, you typically need to be looking for heavy element systems, so large Z systems, where the spin-orbit interaction becomes strong. And so this means looking, I don't know, somewhere down here in the periodic table, these 5D systems like tungsten, rhenium, iridium, 6P systems like bismuth, that sort of thing. Now, on the other hand, if we think about trying to look for the physics of strong correlations, we're normally thinking about going for some sort of local orbital, so thinking up here in these 3D systems, so cobalt, chromium, these sorts of things. Now, we saw, I guess, around a decade ago, a really nice example where this kind of demarcation into strong spin orbit systems and correlated systems broke down. And that was in the physics of the iridate oxalates. And so you can see here, iridium is a 5D system. It's sitting right down here in this strong spin orbit regime, and so you'd think that correlations wouldn't be important at all. And the reason for that is you have these extended 5D orbitals, and you'd expect to have a wide electronic bandwidth that comes from these. And if you take one of the early examples of this, strontium-2 iridium-04, you find that you have 5 electrons partly filling the iridium T2G shell, and so you'd expect a wide band that's well, nearly filled in this case, and so to have just a weakly correlated band metal. It turns out, though, that if you think about the influence of the strong spin-orbit coupling in this system, actually you should be thinking about splitting this wideband T2G state into 2 separate states, the so-called J-effective 3/2 band and 1/2 band up here. Now this 3/2 band is completely filled with 4 of the 5 electrons you have, which leaves you 1 more electron to half fill this J-effective half state, which is now a much narrower band than it was if you thought about this without the spin-orbit coupling. And once you have this narrower band, now correlations can start to play a role again, and you actually find that there's a Mott-like transition of this half-filled J-effective half band here. And so you start with something that you'd think of as a wideband weakly correlated metal, and you find that spin-orbit coupling actually enhances the tendency for this system to become a Mott-insulating material. And so in some senses, it's allowing even moderate correlations to play a significant role because of the narrowing of the band from the spin-orbit interaction. Today, I want to talk, I guess, on the other side of things. So not this idea of taking spin orbit and making narrow bands from that, but rather going to systems which we typically think of more on the correlated end of the spectrum, so 3D and 4D systems. I'll look at cobalt and ruthenium here, where the spin orbit's a bit weaker and we might expect to have stronger correlation effects, and then ask if we can still see the influence of spin orbit coupling in this system. Okay, so the technique that I'm going to be mainly showing you results from today is angle-resolved photoemission spectroscopy. And we already had a nice introduction to photoemission in general in Ben's talk earlier on. And so we saw that this is a photon in, electron out technique. You can think of this as an implementation of the photoelectric effect in solids. Now, actually, a good way to think about this is in 3 steps. So we have our photon coming in, and then we do an optical absorption process. We do a photo excitation from an initially occupied state in our solid into a state that was previously unoccupied. Now the electron in this excited state can now propagate to the surface, but this is a highly excited state, and so this will tend to scatter along the way. And this actually means that photoemission is then a very surface sensitive technique. But still, some of these photoelectrons can make their way to the surface of the material. They're refracted at the potential step at the surface, and then they move into vacuum where they can then be detected. Okay, so we saw earlier that you can think about the conservation of energy in this problem. So if we measure the kinetic energy of the photoelectrons when they're in vacuum, we know the photon energy that we used to excite them, and we can calibrate the work function we should be thinking about here. And then we have a direct measure of the binding energy of those electronic states when they were inside the solid. Now, the extra ingredient we'll be using here as well is to look not just at the kinetic energy of those emitted photoelectrons, but also the angle that they were emitted at from the surface. And if we now use conservation of momentum, we can use this to work out what the initial state crystal momentum was, or at least the parallel component of this. We have a translational symmetric surface, and so the parallel component of the momentum is then conserved in the photoemission process. Now we can do this in a modern detector for quite a number of kinetic energy and angle of emission points simultaneously, and so really start to build up these kind of maps of what the electronic band structure in the solid looks like. And if we do this for different directions in the crystal, so we can tilt our sample, we can rotate our sample, we can then really start to build up a fairly detailed picture of these electronic band dispersions and the Fermi surfaces and constant energy contours that you get within the surface plane. So if you like, the E versus Kx versus Ky dispersion relations of the solid. Okay, and so in that sense, we've got here really a very direct momentum resolved probe of the band structure of materials. Now there's another ingredient here, which is that when we do the photoexcitation process, we leave a hole in the system where we previously had an occupied state, and this is obviously a highly excited state configuration. And we're also sensitive to the processes by which that photo hole is filled, so by the interactions in the system. And so we can look, for example, at spectral signatures of coupling to bosons. You see here a simulation for coupling to a phonon mode, where you get a so-called kink in the dispersion, where you have a reduced velocity close to the Fermi level, and then an increased scattering rate at more than the boson mode energy below the Fermi level. Or you can also look at band renormalizations and lifetime decreases as you move away from the Fermi level due to electron-electron interactions, for example. And so really you should think of ARPES as a momentum resolved probe of the occupied part of the one electron removal spectral function, which tells you then about the electronic structure of your material, and it also tells you something about the many-body interactions at play in your material. Okay, so with that, I'll move to the first of the material systems I want to talk to you about today, and that's the so-called delaphoside oxide material system. And so this has a chemical formula, you can see here, of AbO2. And so in this we have triangular lattice layers coming from a noble metal A-site cation. In everything I'll show you today, this is either going to be platinum or palladium, but you also get copper and silver versions of this. And then separating these A-site layers, you have transition metal oxide layers, and so these are our BO2 layers here. Now, if you're familiar with systems like the perovskites, we know we often find transition metal oxide octahedra in these, but normally these are corner sharing in that case. Here, these octahedra are now tilted over, so they're edge sharing, and your transition metal now also forms a triangular lattice with a triangular lattice of oxygen sites above and below this. Now, actually, we saw in one of the previous, or a couple of the previous talks this morning, some of the transition metal dichalcogenide layers. In the so-called 1T structure of the transition metal dichalcogenide, it's exactly this edge-sharing octahedral type configuration that you have there. And so if you were to take these layers and then just stack these with van der Waals gaps, you'd have one of these 1T transition metal dichalcogenides. In this case, these edge-sharing octahedral layers are separating our A-site metal layers here. Okay, so we can ask what the basic physical properties of these should be, and just thinking in a sort of simple ionic picture for this. So if we first ask about this A-site palladium or platinum layer here, now you find that this A-site, this palladium or platinum, is linearly coordinated between two oxygens here. It comes in a 1+ charge state, which is quite an unusual configuration for palladium and platinum, but it does happen in these delaphosites. And so you'd expect to have a 4d9 or a 5d9 electronic configuration here. And so what this means is if we start to fill up our d orbital energy levels, we find that we now have a single hole in this dz squared shell here that you get from the linearly coordinated nature of this palladium oxygen dumbbell here. And so because we have a single hole in here, you'd expect this to now be a metallic system. And indeed, if you look at resistivity measurements, the ones I'm showing you here are coming from Cliff Hicks. You find that it is a metal. In fact, it's an extremely good metal. You have very high mean free paths at low temperature, on the order of 20 microns or so. And at room temperature, actually, this is even more conductive per carrier than elemental copper metal. So you have a really very nice metallic system here. Now you can see the electronic structure that underpins this, and you can find actually we have essentially a single band system here. We have a Fermi surface which is consistent with this one electron in the DZ squared shell here, and we have these very steep and sharp and crisp bands that you see in here. And in fact, if you look at the quasiparticle effective mass of these bands, you find that this is something on the order of 1 to 1.5 electron masses. If you look at the line width of these bands, you find that these are very sharp, even down to high energies. And I told you a few minutes ago that photoemission can tell you something about many-body interactions in the system. And one of the ways that you can tell that is from the line width. So the line width is then inversely proportional to the lifetime. So the fact that we have a very narrow line width here means that we have a high lifetime in the system, and this is entirely consistent with the very high ability that these carriers have. In fact, in the photoemission here, we're resolution limited. Okay, so how about the transition metal oxide octahedra? So in the system I want to talk to you about today, we have cobalt on this layer. Now we have cobalt on a 3+ charge state, and so you would expect to completely fill the T2G manifold of this octahedral configuration for the cobalt here. And so at 0 Thor, you'd expect the cobalt oxide layer to be band insulating. And in fact, if we now look deeper down in binding energy, we can find some states down here below the Fermi level that are completely occupied, which we can attribute as the cobalt oxide derived states. Okay, this was all for the bulk, but we can also ask what happens at the surface of this material. So as I said, photoemission is very surface sensitive, and so we should see spectroscopic signatures not just of the bulk electronic structure, but also of the surface electronic structure. Now it turns out for this crystal structure, there's no natural cleavage plane here. And so if we cleave a sample, and typically to prepare our samples, we take a sample into vacuum, we cleave it there to do the measurements, you'd expect to find about a 50-50 variation between regions of your sample that are terminated by a single palladium layer here, and regions of your sample that are terminated by a cobalt oxide layer. We can then move the synchrotron light spot around, and we can measure the palladium terminated surface, and actually you can see an electronic structure that already looks very different from the one that we were just looking at for the bulk system before. I don't really have time to talk about this today, but actually this has an instability to becoming an itinerant ferromagnet at its palladium terminated surface. What I want to focus on a bit more for now is the oxide terminated surface, this cobalt oxide terminated surface, where you can see again that the electronic structure we now measure looks very different than the one in the bulk. Okay, and so let's start by asking why this looks different. Now it turns out that the system is a polar system, or the surface is a polar surface. So if we look at the bulk structure a second, you can see that we have now our palladium or platinum layers in a 1+ charge state, and then our cobalt oxide layers in a 1- charge state. And so in the bulk, this just alternates 1+, 1-, 1+, 1-, and there's no problem to this. But at the surface of the material, we do have a problem now. We have now a charged surface, and so we should expect some sort of reconstruction from this. Now, because we have transition metals here that are happy taking different valences, we can think about an electronic reconstruction happening at the surface. And so those of you that are familiar with the strontium titanate lanthanum aluminate interface system, this might look a bit familiar from that context. If you like, we can look at this in a slightly different way. Imagine we have our cobalt oxide layer in the bulk here, and this oxygen above the cobalt here is getting half an electron per unit cell from the palladium in its 1+ charge state, and then the other half electron goes to the cobalt oxide layer above. Now, if we remove this palladium at the surface, we're no longer donating this half an electron per unit cell from the palladium into this cobalt oxide layer. And so we'd expect this cobalt oxide layer to become effectively hole doped compared to the bulk system. Now, we said a couple of minutes ago, in the bulk, the cobalt oxide layer is in a band insulating state. So now at the surface, we should expect a hole dope into that band insulating state. Okay, so if we then look at the measured electronic structure of this cobalt oxide terminated surface, you can see this on the right here. And on the left, you can see density functional theory calculations for the bulk electronic structure of palladium cobaltate. And so you can see several of these features actually match up rather well. We have this steep band over here. This is the one that we were already looking at for the bulk Fermi surface, which you see out here. Actually, along this direction, we have another completely occupied hole band just down here. But then we have these additional states that you see up here crossing the Fermi level, which aren't expected in the bulk for any value of the outer plane momentum. So these we'd attribute then as the states coming from this cobalt oxide terminated surface when we hole dope into this cobalt oxide layer. Okay, let me show you these in a bit more detail here. You can see now, actually, we don't have just one state here, we have a pair of states up here crossing the Fermi level. Actually, if you look at measurements for platinum cobaltate shown at the top or palladium cobaltate shown at the bottom, you find these are rather similar, and that's because these states here, these heavy hole states, are derived from the cobalt d orbitals, and they're not coming from the platinum in this case. Now, another indication that these are coming from these local cobalt d orbitals is that actually you can start to see some spectroscopic signatures of at least moderate electron-electron and electron-phonon interactions here. You can see that as we move away from the Fermi level in both of these cases, the line width is substantially broadened, which means that the lifetime is going down, which is consistent with these interactions. And at the same time, you see a slight decrease in the velocity close to the Fermi level than you have at the down. And so this is due to coupling to a boson mode we expect due to a phonon mode. And all of this together, the already relatively flat bands coming from the cobalt d orbitals, and then the further band flattening coming from the interactions here, means that these states have now relatively heavy quasiparticle masses, something on the order of 10 to 15 electron masses or so. Okay, I'm showing you here now the Fermi surface that we can measure from these cobalt oxide surface states, and you can see maybe very faintly on the outside there's a hexagonal Fermi surface here which comes from the bulk, in this case platinum d bands. And now at the zone center you see a circular and a hexagonal Fermi surface which are coming from these cobalt oxide states. Okay, so the surprising thing now comes when you take a measurement through the Fermi surface here, and you also measure this with spin resolution. And so what you can do is you can do a photo emission experiment. You can excite photoelectrons, you can detect their energy and momentum, and then you can scatter these off a heavy metal target. You can do a process called Mott scattering, or you can do a reflection off a magnetic target to ask what the spin of those photoelectrons is. And under the assumption that the spin of the photoelectron is preserved in the photoemission process, you can then track back to what the spin texture of the initial state was inside the solid. And that's what we're doing in this experiment here. We're measuring the Y polarization of the spin, so vertically on this plot here. And you find that actually these two states have a finite spin polarization, and that it's opposite for the two different Fermi surfaces. So if you look at this Fermi surface on the inside here, you find that this has a a negative spin polarization along Y, and for the outer Fermi surface here, it has then a positive spin polarization along Y. Now, in fact, we can see the same thing if we look at a density functional theory for the surface electronic structure. You can, if you just look here at the arrows for the moment and ignore the colors, you can see that for this inner Fermi surface, we have now a spin pointing up, so Sy positive here, for the outer Fermi surface, Sy negative here. But you find that actually as you go all the way around the Fermi surface, this just cants round, and it cants round the opposite sense for the outer Fermi surface here. And so you have some finite spin polarization of these Fermi surfaces, but one that rotates around as you move around the Fermi surface. Okay, now this is very reminiscent of an effect called Rashba spin splitting. And so let me just tell you for a couple of minutes what Rashba spin splitting is and how it arises. Okay, now imagine you have a two-dimensional electron gas in a material, and imagine it's non-magnetic and you have time reversal symmetry. And so time reversal symmetry tells us that for any eigenstate at momentum point k with spin up, there has to be an equivalent eigenstate at momentum point minus k with spin down. Okay, and so if we have spin up over here, we must have spin down over here. Great. Now let's say we also have inversion symmetry. For any eigenstate now at momentum point k with spin up, we must have an equivalent eigenstate at momentum point minus k with spin up. So under inversion, we move momentum to minus k, but we don't flip the spin. So now our spin up here must have an equivalent spin up over here. And so if we take these two constraints together, we say we've got time reversal symmetry and we say we have inversion symmetry, then that means that all of our states of this 2D electron gas must be spin degenerate. We have spin up, which means spin down, and spin up, which means spin up. And so these must be spin degenerate. Okay. Now let's say that we break inversion symmetry in the solid. And so one way to think about breaking that inversion symmetry is to take your 2D electron gas and apply an electric field normal to that electron gas. Now thinking semi-classically for a moment, in the rest frame of the electrons, that electric field is transformed to an effective magnetic field for those electrons. And that magnetic field can Zeeman split our electron states. But now this will be with opposite sign at opposite momentum. And so if we imagine applying this electric field and breaking and turning up its strength, you'll find that our original 2-deg states start to split apart, and this is now a spin splitting here, and we have our spin up states and spin down states now separated in energy, but we still have time reversal symmetry in the system, and so if we go to negative momentum, we must have exactly the opposite of this. Now, if our electric field is applied along the normal direction of our electron gas, if we just take a spin orbit Hamiltonian, we can see that this transforms, as you can see here. And so we now have a locking between our momentum and our spin, with the spin locked perpendicular to the momentum. And so you can see how that works on this Fermi surface over here. We have the electron, the spin down over here, and then as we go around our Fermi surface, we have spin up over here. And so we have exactly this same sort of chiral spin structure as the one we found experimentally for this cobalt oxide surface state. Okay, and so this looks very much like it would then be an influence of spin-orbit coupling in the solid combined with the broken inversion symmetry that you get at the surface of a material quite naturally. The surprising thing is exactly this thing I was mentioning at the beginning of the talk, that if we think about having the local cobalt 3D orbitals here, you'd think that spin-orbit coupling was really rather modest. And it turns out that for these Rashba spin splittings, typically the energetic splitting you get here is much smaller than the atomic spin-orbit coupling in the solid. And actually, you can see that if you look at this example on the left. So this is so-called a giant Rashba compound, bismuth telluride iodide, where you find here an energetic splitting here, which is on the order of only 20% of the atomic spin-orbit coupling in the solid. So given that, and given the relatively modest atomic spin-orbit coupling of a cobalt-3d orbital, you'd expect this effect to be rather negligible for our cobalt oxide surface. But actually, if you look here, you find a splitting in momentum between these two states, which is actually just as big as in this so-called giant Rashba compound, bismuth telluride iodide. So this really isn't a small effect. And in fact, if you trace this spin splitting all the way down to a high symmetry point of the Brillouin zone, you can see these bands remain spin split all the way down here. You can get a good quantitative estimate for the size of the Rashba spin splitting in this system, which turns out to be about 60 millivolts, which is actually really the full atomic spin-orbit coupling strength of a cobalt-3d orbital. And so it seems that somehow, even though we're dealing with these local d orbitals that have modest spin-orbit coupling strength, because we're getting the full energy scale of that in spin splitting these states, this is really quite a pronounced effect here. Okay, let me just go quite briefly through the reason why you get this strong effect here. And maybe to show that first, I should start with a sort of conventional picture. So imagine you have a set of degenerate energy states in a solid. Now, if you have a significant spin-orbit coupling, you'd expect to make states of well-defined total angular momentum, J1 and J2, split by that spin-orbit coupling. Now, if we apply our inversion symmetry breaking potential as a relatively weak energy scale in the solid, so in other words, now we take our surface and we think about applying an electric field at our surface because of the broken inversion symmetry. Now you'll split your states into spin up and spin down states, just as we've seen in our simple model for a 2-day. Okay. And this energetic splitting between these two states will really be limited by the energy scale of this inversion symmetry breaking field. Okay. Let's think about this another way around for a second, and let's say we have now a very strong inversion symmetry breaking in the system. We'd expect now to split our states into states of well-defined orbital angular momentum now. So we allow new orbital mixings by the inversion symmetry breaking that we have in the system. And now, if these states are sufficiently far separated on the scale of the spin-orbit coupling, we can't mix states of opposite orbital angular momentum with spin-orbit coupling anymore. So now if we turn on spin-orbit coupling, all we can do is align our spin either parallel or anti-parallel with that pre-existing orbital angular momentum. And then we get an energy splitting here that's now the full strength of the atomic spin-orbit coupling in the system. And so I guess the key message here is if you can somehow force a very large energy scale associated with the inversion symmetry breaking in the system, then you get a spin splitting now which is as large as it can be. And that seems to be the situation here. And actually you can understand this on the basis of a rather simple type binding model for the cobalt oxide surface layer here. So this is just taking a monolayer of cobalt oxide, and you can see in here that your dominant hopping pathways are either directly between the cobalts, but because we've got local orbitals, this is not such a significant effect here, or they can be through these oxygen sublattices either above or below the cobalt plane here. Now, if we had inversion symmetry in the problem, these hopping paths would have to be equivalent. But because we don't have inversion symmetry, these hopping paths can vary. And it turns out that at the very surface of the material, you have a strong energetic shift of the density of states of the oxygen orbitals there, because there's a loss of this chemical bonding to the palladium. And this causes the hopping to be very strongly favored through this surface oxygen layer here than through this subsurface oxygen layer. And so it's really making the conduction electrons themselves feel this very strong influence of the breaking of inversion symmetry in the system. Yeah, I won't go through in too much detail here, but you can do a semi-quantitative estimate of this on the basis of the tight binding band structure here. And you find out that the energy scale associated with breaking of the inversion symmetry is on the order of 150 volts here. So about twice the strength of the atomic spin-orbit coupling. And so what that means is that even in a system where you don't have a very strong atomic spin-orbit coupling itself, by finding ways to maximize the energy scale with which the inversion symmetry is broken here, you can actually recover the full energy scale of the atomic spin-orbit coupling in spin splitting your electronic states. And so you get a Rashba splitting that's much larger than you might have naturally assumed would happen in this system. Now, actually, a kind of nice thing here is you would typically imagine that as you went up to a heavier element system and you went to stronger spin-orbit coupling, you'd tip yourself over into this regime here, where the spin-orbit coupling is dominating in the problem. And so you now have a vanishing return, if you like, of increasing spin-orbit coupling. Your spin splitting won't keep getting larger. Now, actually, because of the way that the inversion symmetry breaking is coupled through these hopping pathways here, this energy scale also increases as you increase the bandwidth. And so you can go up to stronger spin-orbit coupling systems, heavier element systems, and you increase the effective energy scale associated with this inversion symmetry breaking as well. And actually, to show that, you can see here that if you go to a 4D analog, this is now palladium rhodate, you still recover the full atomic spin-orbit coupling strength in spin splitting these electronic states. And that's, in this case, about 150 millivolts, which is really a giant spin splitting to be having in any material, and I'd say in particular in an oxide material. Now, I think we were interested in this from studying the fundamentals of how these spin splittings result. But I should say there are various schemes in spintronics, things like data-das spin transistors, which rely on generating exactly these sorts of Rashba spin splittings, where then a key criterion is what's the momentum splitting of these spin split states at the Fermi level. If you like, this tells you the precession length for an electron that would be precessing as it moves through a channel made of this material. And so these really giant effects here potentially give you routes towards controlling spin precession, and to doing Edelstein effects for spin charge conversion and that sort of thing. Okay, can I check how I'm doing for time, Simon?
Yes, it's a little tight. So you had about 38 minutes, Phil.
Oh, crikey. Okay, sorry, I went for far too long in that part of it. I wanted to also tell you about another system which seems completely different, but in the end has some similar physics cropping up, which is calcium ruthenate, which is a bilayer oxide system. Maybe let me just very quickly say that this is a pretty interesting material, which is a bad metal at high temperature, but then has some magnetic phase transitions as you cool it down. And one of the key features is that as you go from well, 56 Kelvin is the Nell transition. Then at 48 Kelvin, you have a spin reorientation transition where the spins move from pointing along the A-axis to pointing along the B-axis, and at the same time there's a structured transition. I will just skip through here for a second. If you look at the electronic structure in this system, you find quite a complicated low energy electronic structure. But this doesn't vary much at low temperatures. This is all the way up to this structural and spin reorientation phase transition. But you find as you go through this spin reorientation transition, the electronic structure changes quite dramatically. You move from having these M-shaped type states here to having now hole bands that go straight through the Fermi level up here. Now I will, yeah, maybe I can just very briefly say that the this change in electronic structure is really due to a loss of hybridization that you get between two sets of states that cross over each other at the Fermi level. So in the low temperature state, these have a finite band gap, whereas in the high temperature state, these no longer have a finite band gap here. And if you actually trace through calculations, what's the origin of this band gap opening, you find that it depends on the orientation of the spin moment that you put in the calculations. So if you have the spin pointing along B, you get this band gap. If you have the spin pointing along the A axis, you now have these bands crossing through each other. And in fact, if you trace this gap, you find that it opens as soon as you count the spin anywhere away from the A axis here. So if it's along A, you have no gap, and then it opens with a kind of cosine form as you count it towards B. And you'll see that this actually looks rather like this Rashba Hamiltonian we had before. So now you have a gap that opens that depends on S cross A, which is rather like this Rashba Hamiltonian if we had some effective electric field in the system now pointing along the crystalline A axis. And it turns out that a structural tilt mode that you have in the system, it gives you exactly this sort of electric field now pointing along the A axis in the system. And so this Rashba type physics that we were talking about before, giving these spin split states at surfaces, can actually be at play in the bulk of materials as well. And in this particular case, it allows an electronic band gap to open at the Fermi level as soon as you count the spin away from the crystal A axis here. And so we think that that's really what's going on in this calcium ruthenate. But the interesting part of this is that actually this gives you a route to generating energy gain by moving the spin away from the crystal A axis. So you can imagine in this system that there's some magnetocrystalline anisotropy that causes the spin to point along the A axis at the nail transition. At sufficiently high temperatures, it doesn't really matter if you're opening up a band gap at the Fermi level or not. There's no energy gain for that. But as you cool the system down, there now becomes an electronic incentive to open a band gap at the Fermi level here, which you can do by causing the spin to rotate to point along the crystal P axis. And so in fact, then there's a kind of Rashba-driven origin for a magnetic phase transition that happens in this system. Okay, I'm sorry I spoke for too long on the first part of the talk. I wanted to say a bit more about the second, but I'm certainly happy to talk to people more about this if there are questions. But I guess in general, what I wanted to try and get across is that where you have inversion symmetry breaking, either at surfaces or in the bulk, you have a couple of different routes in order to really try and maximize the influence of spin-orbit coupling in systems which you would typically think of as sort of more correlated in nature. And that really we should be thinking about spin-orbit coupling on a fairly equal footing with the kinetic terms, with correlation terms, in maybe a wider spectrum of materials than we always do. So with that, I'll thank you for your attention, and I'm happy to take any questions.
Thanks, Phil, for a beautiful talk. We open the chat up here. Okay, so remember again, please, if you have questions for Phil, put them into the chat. Here we go. There's one from Oliver McHugh. Oliver.
Hi, thanks for the talk. I was just asking, is there a way to break inversion symmetry without invoking the use of external fields?
Yes, absolutely. So any time you have a surface, then inversion symmetry is broken naturally. So, you know, imagine you've got some bulk material which has inversion symmetry, and now we terminate that with the surface. Now, if you transform R to minus R, anything in your crystal to outside of your crystal, you no longer have inversion symmetry there. So the surface is a very natural way by which it's broken. You can model that in many cases as an effective electric field, but just the very act of having the surface there breaks inversion symmetry to begin with. But you could also have structures that intrinsically don't have inversion symmetry themselves. They're not centrosymmetric structures. So if you have some material where you've got an atom at site R and you don't have that same atom at site -R, then you no longer have inversion symmetry in that crystal structure. And so then all of these effects get unlocked in the bulk. It turns out that in this this calcium ruthenate, it's a bit more complex than that, because you do have an inversion center in the crystal here. But if you look locally on each, if you like, subunit of the crystal, you have an effective dipole, so an effective electric field pointing to the right and pointing to the left here. And so you can also have sort of local versions of this symmetry breaking, which are kind of hidden in your structure, even if the overall structure, if the space group of your structure is centrosymmetric.
Thank you.
Thanks, Chris Spell. Chris, you have a question?
Yeah, it kind of follows on from Oliver's question, actually. If you spoke about like LAOSTO type things happening at your cobalt palladium surface, where you transferring charge or something like that. Yeah. In that field, of course, there was also fighting about are there structural things happening, and at the surface you could have a structural distortion or a structural reorientation, reconstruction. And is there any evidence for any of those things?
Yeah, so there's not in the palladium cobaltate. I think so. Okay, a couple of things you can look at. One is the electron count. So if you, sorry, let me go back here. Sorry, let me try and just find the slide. So one of the things that you can ask about is what's the charge carrier density of your. Okay, my Outlook seems to have my thing has more or less completely crashed. Sorry. So if you look at the volume of the Fermi surface here, so for those that don't know, one of the things you can do directly from photo emission is to look at the area of your Fermi surface and then extract an effective charge carrier density, so from a Luttinger volume of the Fermi surface there. If you do this from these surface states, you find something pretty close to half a hole per unit cell, which is what you would expect if you had the simplest electronic reconstruction there. You can also look in measurements like low energy electron diffraction, so surface structural measurements. Is there a change in periodicity? And there's no apparent change in periodicity here. My guess is there will be some defects around, but it doesn't seem to be the dominant cause of the physics in this case. It seems to actually be a relatively clean example of a kind of pure electronic type reconstruction.
Okay, got it, great, thank you for that.
Bill, if I can ask one final question, are there magnetotransport measurements on the calcium ruthenate? Because it seems like that would be particularly interesting.
Yeah, there are magnetotransport measurements there. It ends up as a relatively complex case because you actually have antiferromagnetism, so you have ferromagnetic coupling within a bilayer. Then it's antiferromagnetically coupled between the bilayers. And so there's a lot of there's sort of spin flop transitions that happen as you apply fields to this, and you also have some Deljinsky-Maria interactions that come in, and you get spin spiral phases in there, and so it ends up giving you a pretty complicated phase diagram in magnetotransport. But yeah, there's a set of measurements there.
Okay.
I think maybe in the direction that your question is going, an interesting thing is whether you can tip these phase boundaries around by applying fields in order to encourage already the spin canting at lower temperatures, say, than it occurs experimentally.
Okay, great. Well, we're out of time, so let's thank Phil again for a really beautiful talk.
Thanks.
Thank you. Jared, I think you're taking over now, is that right?
So next up on the billing, we have Chloe. Chloe, are you going to be ready?
Hello, sorry, I didn't unmute myself.
No, it's fine. Sorry, I was just laughing at your background. So, yeah, Chloe's going to speak to us about indistinguishable photons from organic molecules.
Cool. Thanks, Jared. Okay, yeah, so moving on to what I do in my PhD. Now, my aim is to theoretically model these single photon sources, and in particular, we're looking to create this ideal photon source. So what is an ideal photon source? Now, there's three main characteristics that they have. The first is you want it to be deterministic. So that means that you want the photons coming out to, every single time you press the button, there's a photon that comes out. So it's 100% of the time that you're getting photons. Next up, you want the photons that are being emitted from the source to be indistinguishable. And that means that subsequent photons, if you interfered them, you'd find that they have exactly the same polarization, the same temporal profile and spatial mode. And then finally, you want high collection efficiencies of these things. You want to make sure that there's a lot of photons coming out of these sources. Okay, so moving on now to the motivations of my work. Now, single photon sources are useful for many quantum information applications. The first of these is quantum computing, and this is the one that I am kind of focusing most of my efforts into achieving. And it was found in 2000 by Neil that you can use photons for optical computing, and it's where the photons are the qubits in this case. So next, you can use them for quantum key distribution, where quite a few protocols use photons in their methods, and this is how you can distribute secure information. So it was theorized that you can create a very, very secure method of cryptography, which could create a more secure internet. And then finally, we have quantum sensing, which is where you can achieve more precise measurements than possible in classical methods. So I believe this was used at places like the LiDAR to detect gravitational waves. So in particular, the source that I've focused on for most of my PhD is a single organic molecule, and this is called DBT, which is shown here. Now, the reason why people care about this source is for quite a few reasons. The first is it emits in the infrared, which is quite a desirable emission range at 782 nanometers. We can see here that this is the emission spectra from one of these sources. So we've got the strong emission at 782 nanometers, which corresponds to the zero phonon line emission. So I'm going to use that term probably quite a lot. And that's when you have the population being the excited electronic state, and it decays down to the ground state, and there's no kind of manipulation into a phonon mode at all. You also have some other features in this emission where you've got broad sidebands that you can see overlapping the zero phonon line, and these 4 spikes, and these come from various phonon characteristics of the crystals. So we also have the fact that these DBT molecules are lifetime limited at low temperatures. So what that means is that the emission into the zero phonon line at this 782 nanometers is purely coherent at these low temperatures. And so that means that there's no pure dephasing, which is when you can have kind of shaking of these excited states, and you can have virtual transitions to phonon modes, which can decohere your photons. We also have that they're tunable over the inhomogeneous range, and what that means is if you were to get 2 DBT molecules and look at the photons, because they are molecules in themselves, they're going to have very similar emissions. They may differ by about a nanometer, and by using the Stark effect, so by tuning them with an electric field, you can overlap these emission frequencies, which is quite desirable, as many sources use things like multiplexing to create separate sources effectively from one. And then finally, we have that these are photostable, and what that means is that you can excite them 10 to the 12 times before they photobleach, which is when their structure is irreversibly changed and they don't provide these emission properties. So I'm not actually going to go through this work that is flashed up on the screen today. This is a publication by myself and collaborators from Imperial and also Sheffield, where we in detail described a theoretical model which captures the emission spectrum of these molecules. And you can see here, this blue line is the fit to the emission spectra, which is taken from Kyle, Ross and Alex at Imperial. However, I want you to agree with me and kind of go with the fact that I can calculate this emission spectra because I'm going to be using this for my results. And I explained a little bit more about how these results were found on the poster earlier today. So the kind of key thing that we really care about is how to achieve indistinguishable photons. So this is the emission spectra again. And as I previously mentioned, what you really want to keep is the coherent part of the emission in the zero phonon line. So that means that you don't want any of this stuff sitting out above 780, let's say 3 nanometers and above. So there's 2 ways of achieving this. Firstly, you can just filter. So you can filter out these peaks that come from phonon modes and the DVT molecule itself. And then you could also, you want to filter out this sideband because this is also incoherent. The next approach would be to couple it to a photonic cavity, which is a little bit more involved in terms of the experimental effort. And you can have some really fun effects with this, as you can actually enhance the zero phonon line if you couple strongly enough. And there's certain regimes that you want to sit in order to achieve your maximum indistinguishability. So if we're just looking at the emission here at 2 Kelvin, so using the model to calculate the emission spectra, if you scale it back to 2 Kelvin, it has been calculated that the indistinguishability of this molecule will be 0.31. So that's if you're including all of these side peaks. And then if you filtered off the 4 vibrational modes and you're just considering the sideband and the zero phonon line, you would have an indistinguishability of 0.51. So this is okay already for things like quantum key distribution, where you use quantum repeaters to enhance your signal. However, because I'm focusing on trying to aim for quantum computing, you really want to get near unity values. So I'm now going to go through separately filtering and then what happens when you put it in a cavity. So firstly, the filtering case. So it was proposed by collaborators at Imperial who are doing all of the experiment that we could use 2 filters to really cut off all of the incoherent junk from the spectra. So the first one is going to be applying a bandpass filter, which is one that you can just buy off the shelf. And the manufacturer data says that it's 785 plus or minus 3 nanometers. And this is a scan from the actual filter itself that was taken by Ross. And I've moved into inverse picoseconds, sorry about that, they're kind of a theorist unit for this field. So everything's going to be changing to now a detuning. So 0 is when you're looking at zero phonon line at 782 nanometers, and then you're detuning by a certain amount. The next filter that we're going to apply to the emission, so you first pass it through a bandpass, then we're going to pass it through a Fabry-Perot filter. Now, this is what the structure of that filter looks like. We have a series of teeth that have a width of 4.2 nanoseconds, inverse nanoseconds, which is very small if you compare that to the size of the zero phonon line itself. And then we have a free spectral range of 0.062 inverse picoseconds. So that's the space between the teeth. And you can see here at 0 detuning, all of the light is being let through at this width of 4.2 inverse nanoseconds. So looking at what this actually looks like when you consider the emission spectra, we have in this figure here, the orange line is the calculated emission spectra without any filtering. The blue line is what happens when you pass it through a bandpass filter. And the red line is what happens when you pass it through both. So you can see that these teeth are cutting into the sideband, but because this is on a log scale, they're really depreciated. But you hold on to most of the zero phonon line emission. So looking at the first way of optimizing this situation, now the Fabry-Perot filter doesn't really need to be optimized because it's already set on 0 detuning. so the experimentalists can just tune that. However, with the bandpass filter, because it's already a bit off of 782, we can shift this and optimize the indistinguishability. So what I've done is set the model of the emission spectra to 4.5 Kelvin, and we can see here what this looks like. So the orange line is it without any filter, and the purple line is what happens when you pass it through a bandpass filter. And I want to consider what happens to the indistinguishability when you detune the bandpass filter by a small amount. So this is a little bit of maths. I don't have too much maths in this presentation, but what this is the calculation for finding indistinguishability. So we've got FBP is the bandpass filter function, and that has been taken from an interpolating function of the actual data. And then ZPL and SC is a sideband and the zero phonon line emission, respectively. And the reason why there's no sideband emission in the numerator is because it's incoherent and therefore doesn't contribute. And this is on top, it's a 2-color spectrum. So that can be calculated via previous methods. So what I'm showing up now is how changing the detuning of this bandpass filter changes the indistinguishability calculated. So this is at 4.5 Kelvin, and we found that at minus 2.41 inverse picoseconds is where you get your maximum. And you also have to consider efficiency here, because if you scale it completely off, then you're going to lose all your efficiency. So this, we made sure that the realms in which we were searching this were in kind of the top hat of the bandpass function, as shown here. So looking at what we find from the indistinguishability now, we've got the orange line shows the filtered emission with both the bandpass and the Fabry-Perot, and we can see how by changing the temperature down to 2 Kelvin, you can reach near unity values, and it's shown here that it can go to 0.997, which is really good. And if we're considering now the efficiency, this is the power of the filtered emission over the power of the unfiltered emission. At 2 Kelvin, we have a cropping off of, well, we keep 22% of your emission. And this is okay because these sources will emit many, many, many photons. So this shouldn't affect the validity of any of these sources as a single photon source for computing. Okay, so moving on next to the microcavity results. So this is a bit more involved now in terms of how to model these systems, but I've not gone into too much maths. I'm hopefully just going to explain the main results and what we've done. So the microcavity that is being currently designed and built in Imperial, led by Carl Major at Imperial. Sorry, I said that already. It's shown here in the picture. So it consists of optical fibers that are fed in through this V-groove array, and they are aligned to concave mirrors that have been plated with a dielectric Bragg reflector. And inside the space between the mirror and the optical fiber is where the cavity mode exists. And you can dope this system with your DBT molecules. So the particular parameters they cared about and they wanted me to look at were a coupling strength of 0.62 inverse nanoseconds. And this is quite weak when you consider cavity coupling. And the reason why you don't need to go too strong for this is because we're going to work at the low temperature range where we're going to already be in a lifetime limited regime, so you don't need to enhance your zero phonon line too much. The cavity width is a little bit broader than the width used in the Fabry-Perot filter before, and this is now at 0.01 inverse picoseconds. So using these results, I then calculated the spectra, passing this through a cavity, and these calculations are a little bit more involved than calculating just the plane emission spectra. I have them in the supplementary at the end. And we can see here that it's quite similar to just the filtering effect. So we've got the cavity emission in purple, where you can see the sideband is very much suppressed, and you've actually cut off some of this zero phonon line. So it's really not enhanced at all. There's no cell enhancement. So looking at firstly the efficiency results, this is considering the power of the detected cavity emission over the power of the bare emissions, the emission without any cavity coupled to it. And we can see that for the case where you consider both the zero phonon line and the sideband, we have an efficiency of 0.27 cent, which is higher than the previous case. And that makes sense as the cavity width is not as small. And then I looked at the case for just having the zero phonon line as well. So when if for example, you can filter out all of the sideband emission, which would be quite difficult to do, so integrated. So leading on to finally the indistinguishability results. Calculating the indistinguishability is quite similar to the previous case, where we've made some assumptions from the fact that we're in a weak coupling regime, and that is that the cavity modes, which are alpha here, can be modeled as a filter function, where this is just the Lorentz filter using the cavity width kappa c, and the dipole operators of the two-level system of the DBT molecule. And if you calculate this, so it's very similar calculation to before, we get the following results, where at 2 Kelvin, we've obtained the indistinguishability of 0.996, which is again quite close to unity. And you can see how this decays over temperature, where obviously as your temperature gets higher, you have more purely phasing in your zero phonon line, which decoheres the photons, and your sideband grows. So that broad sideband gets larger as the phonon from the bath interacts more. So moving on finally to future work, I think I'm in good time. I want to try some more filters and see if I can get some good results for indistinguishability without too much effort from the experimental side. And I also want to optimize, I've already started doing this, optimizing the cavity parameters for G and kappa. So this is quite a hard one to ask the experimentalists to change because some parameters are quite hard to reach for. However, it would be nice to have a theoretical kind of map of where the areas for high indistinguishability are going to live. So that's all I'm going to say today. Thank you very much for listening. And yeah, leave a comment in the chat box.
Well, thank you, Chloe. It's a really interesting talk. There's no questions in the chat currently. And we're running a little bit close for time. But
Yeah.
I was just going to ask, because I'm chair, so I'm just going to ruin the timings even worse. Is there like a particular reason why you're using your DBT photon source over semiconducting quantum dots or any of the other?
Yeah. So, okay, so quantum dots have the best kind of like results at the moment. So a group in China have done a 14 boson experiment, which is really hard to achieve. However, you have to use one, when you make quantum dots, they're all different. You can't make them the same. They don't have the same emission. It's hard to tune them. So if you want to have a system with many qubits, you're doing that from one quantum dot, which means that the photons that come out of it have to be multiplexed, which is a lot of effort. So the idea and the reason why people care about molecules is because the fact that they are a molecule, they're going to be emitting the same each time. So hopefully the big goal is to end up having, like, in that microcavity, to have various different sources all tuned to the same emission, such that you don't need to multiplex, you just have many sources. And there's quite a few other kind of pros and cons for all sources. There's NVs as well, and then you've got like superconducting qubits, which was spoken about earlier. But people are just working from all angles, trying to get the best result effectively. But yeah, thanks.
No, that makes sense. So yeah, thank you again for your talk.
Cool. No worries.
Next in the order is Becky.
Let me share.
Cool. So yeah, this is Becky's talk on the epitaxial engineering of metastable uranium metal.
Yeah, so today I'm just going to talk to you a bit about my work with uranium metal thin films, and in particular about the technique of epitaxial engineering and how we're using that to essentially lock in unusual phases of uranium metal. So this is just an illustration of two of the surfaces that we've been depositing onto and how they have quite a close lattice match with HCP uranium, which is a phase that doesn't exist in bulk. So I just want to talk to you a bit about why we're still interested in uranium metal. You know, it's an element, why don't we know everything about it yet? And in particular, how we stabilize these metastable phases as thin films. And in particular, I want to talk about thin films of strained alpha uranium and HCP, which are what we've grown more recently, and some of the diffraction studies we've been doing on these. So I need to thank Lottie for doing the most recent scans. And then, of course, just looking toward the future and how we are going to try and attain single crystals of these materials. So first, we need to take a look at the actinide series. So it's arguably the weirdest series in the periodic table, and that's all thanks to the 5F electrons. So along the series, the 5F electrons, they progress from being more itinerant to more localized at the heavier end of the spectrum. So in this transition region here, where the 5F electrons are kind of teetering on the border, we end up with some pretty unusual effects. So there are two major things that happen in this regime. So if we take a look at the all of the structures that we can find in this regime, we see a lot of unusual ones in quite a narrow temperature regime because this 5F band is quite narrow. And the other important thing to consider are the electronic ground states. So as we traverse the series, we tend to go from more superconducting behaviors towards magnetism. So obviously you can expect that in this regime here, we're going to see some pretty unusual behaviors arising, and that's where uranium sits. So uranium has three bulk phases. So you can see the phase diagram over here. So alpha uranium is an orthorhombic phase. It's the one that's most stable under ambient conditions. And this one's relatively well studied. So we know that it hosts several charge density wave states below 43 Kelvin. But as we go up in temperature, we encounter the beta phase, which is really complex. It has more than 30 atoms in the unit cell, and we don't quite know why it likes to form this structure. Go up again, we see something a bit more familiar. So that's gamma uranium in the BCC phase. And this could be a nuclear fuel interest because it actually expands isotropically, unlike alpha uranium, which has some pretty strange thermal expansion coefficients. But what's particularly interesting is if we consider the relaxation from the gamma to the alpha phase, it's been proposed that there's a phonon mode that allows it to pass through a hexagonal close packed phase. So this is the one that we've been focusing on. We've actually locked this in as a thin film. And kind of the overarching theme of my PhD is to try and stabilize single crystal thin films of HCP and gamma uranium. And that's essentially because when we try and grow these crystals in bulk, cooling through all of these phase transition causes a lot of fractures and defects, and we end up with a lot of multi-phase samples. So these two phases here have never actually been stabilized in their pure form as single crystals. So just a bit of a diversion as to why these materials are still interesting. So a lot of you have probably seen a Hill plot before, where we look at the uranium-uranium spacings in a whole bunch of uranium compounds. And we see that the uranium spacing is what's crucial for determining the electronic ground state behavior. And so we look at this crossover here at about 3.5 angstrom, where the materials transition from displaying more magnetic behaviors to superconductivity. So all of the phases that we're interested in, the metallic phases, lie down at this end of the spectrum here. So what's particularly interesting to note that even if we could change the uranium separation within each of these phases, we could have a pretty significant impact on the behavior of the ground state, particularly as it's lying quite close to this transition region. So just keep that in mind while I talk about what epitaxial engineering is and how it might have an impact on these parameters. So when I talk about thin film epitaxy, I just mean that we're depositing thin layers of uranium metal onto a single crystal substrate. So ideally, we'd find a substrate that has really close lattice parameter match to uranium. It could be in one direction, it could be in multiple. And if this lattice match is close enough, it's energetically favorable for this uranium overlayer to strain itself to adhere to the substrate. So obviously this is going to have some impact on the lattice parameters of this uranium layer, so that could impact the electronic ground states. Unfortunately, there's not that many substrates that have any matches with uranium. So what we can do to open up some more avenues is to basically insert a buffer layer in between the substrate and the uranium. Obviously, this is just a 2D cartoon. So in reality, the system's a lot more complicated, but we can use these buffer layers to reduce our interfacial strain. And we tend to use the BCC refractory metals like niobium, tantalum, and tungsten. But the domain orientations, they're quite complex. So this is just tungsten 110 deposited onto A-plane sapphire. So the situation gets quite complex when we actually look in 3D. And it turns out that the choice of buffer layer and the temperature that we then deposit the uranium down onto this buffer layer is absolutely crucial for what phase of uranium we end up growing. So just to kind of hammer home the point, these are all films that we've grown using our deposition kit in the past. So if we put down a niobium buffer in the 110 orientation, we just tend to grow something that's quite like bulk alpha uranium. The charge density wave is around about 43 Kelvin. If we then keep everything the same, but just switch it out for tungsten, we end up with strained alpha uranium. So in the plane of the film, the A-axis is actually under tensile strain, so it's larger than in the bulk. And this has the effect of driving the charge density wave transition temperature up to around about 150 Kelvin. So we've been doing some, if we increase the temperature even further and go through to HCP uranium, we actually see there might be a possible charge density wave transition around about 100 Kelvin. So we've been doing some measurements on this. So we looked at the Hall coefficient at low temperatures, and we see there's actually a change in sign of the Hall coefficient around about 100 Kelvin. And this is actually pretty similar to the behavior that we see in bulk alpha uranium as it undergoes this charge density wave transition. Something we've also seen is the potential for growing BCC also onto a tungsten buffer layer. But we need to improve our heater capabilities before we can try and grow those. So the ones I mainly want to talk about today, we've grown some samples that are in this regime, and they seem to have some kind of strange behaviors going on. So I just want to talk you through some of the diffraction studies that we've recently done on these. So some of this is quite new data. So of course, this is just high angle X-ray diffraction. So we send our X-ray beam in, and it will diffract through the lattice. And from that, we can look at the outer plane lattice parameters of our sample and determine what phases are present. So here we see the alpha U002. This is the alpha uranium under tensile strain in the plane. So you can see that's the major component of our film. But we've also got a few of these parasite phases of unstrained alpha uranium and a tiny bit of HCP over here. So what's particularly interesting to take a look at, so this is our low temperature sample, and the tungsten 110 peak actually has these reflectivity fringes. So essentially when we send our X-ray beam in, it will reflect from the interfaces if we've got a layered system. And if these interfaces are really high quality, we should see an interference pattern coming out at the other end. And that's exactly what we see here. But what's interesting is that we've lost a lot of the intensity at high angles, which probably means there's going to be some strain at our tungsten uranium interface. So perhaps we've got a highly strained layer of alpha uranium on top of our tungsten 110. So how do we check what the quality of our layers is? So to do that, we can do rocking curves. So in this, we fix 2 theta and we just move omega, and that tilts the scattering vector into the plane. So we can look at the mosaic spread of our samples. So this is just a rocking curve of our tungsten layer, and obviously it's really narrow. We know we've got some fantastic quality tungsten layers down. So that's all good. So we could have a look at our alpha uranium layer 2, and we see that we've also got a really narrow rocking curve for this low temperature sample. So that's really great. It kind of supports our hypothesis that we've got a strained alpha uranium layer, and it's totally strained with the tungsten. However, we've grown a slightly higher temperature sample, and this rocking curve then starts to look somewhat deformed. So we're thinking perhaps something's happening at this interface as we go up in temperature. And we can have a little guess at what's going on there by looking at another high angle scan of this high temperature sample. So this is just the same data again, but just a bit higher quality. So this blue one is our cooler sample here. We can see the loss of the fringes on this side, but actually, as we increase in temperature, we seem to regain these fringes at the high angles. So possibly there's actually been some strain relaxation at this interface. And that might be in part due to this HCP phase. So we're thinking there might be a thin layer of HCP forming at the interface and kind of ruining that nice strained alpha 002 layer. So just for completeness, we've got one more sample that's even higher temperature than that. So this is this guy here in red. So we see that we've got HCP phases dominating here. And what's interesting is that we've got this almost 2% shift in the C lattice parameter, so suggesting HCP is probably quite a malleable phase. And something else, of course, we've been looking for as well is BCC uranium. So we're thinking this here might be the BCC 110 peak, again with some reflectivity fringes. So maybe we've got a very thin layer at the interface. So that's all interesting, but what we really want to do is try and isolate the HCP and the BCC phases. And obviously this is looking quite tricky on tungsten 110, so we need to explore other avenues. And one of these that we have discovered recently is that copper 111 and HCP uranium have a fantastic lattice match, so it would extend throughout the entire film. And we actually managed to grow this just onto glass, which is quite impressive at room temperature. So now we're trying to work out how to grow single crystals of copper 111. And apparently you can do this on C-plane sapphire at relatively low temperatures. So this would be a very interesting low temperature route for the growth of HCP uranium. So one final phase, BCC uranium is very elusive. It's been stabilized with molybdenum, but never as a pure phase. So one of the papers actually that came out of Bristol recently from the theorists, they mentioned that an experimental group had grown BCCU possibly by accident. They'd reported it as alpha, but it looked more like a signal from a BCC thin film. So I had a look, I thought that's a bit crazy. But actually they grew onto permalloy and they actually have very similar lattice parameters to BCC uranium. So if we could grow a single crystal of permalloy and deposit BCC on top, it probably wouldn't, obviously it wouldn't be fantastic for transport measurements, but possibly looking at the band structure via ARPES, where we only need the first few layers, that could be a really interesting avenue to go down. So that's all for now. So if anyone's got any questions, please let me know.
Thank you, Becky. That was really interesting. No questions. Oh, there is. Okay, Phil?
Hi, yeah, thanks for the nice talk. I maybe missed this, but what thickness are you growing to here, and do you see any strain relaxation setting in with increasing thickness?
We haven't tried any thickness studies yet. These the uranium layers are 36 nanometers, and the buff layers are about 18 nanometers, so they're quite thin films. So I think of the strained alpha uranium, there have definitely been some huge ones grown. I think 500 nanometers. Papers have been published on that.
Okay, great. Thank you.
They're still strained.
I might ask a question. This is probably a number you either have on the top of your head or you don't. But when you were talking about the copper 111 plane having a lattice mismatch that was really small, how small is really small?
I think it's 0.64%.
Okay, yeah.
So it's less than 1%. Yeah.
Cool.
Which is a pretty good lattice match.
Yeah. How are we doing for time? Okay, well, if there's no other questions, thank Becky again. It's really weird doing that alone. And move on to our next speaker. Will, are you ready to present?
Yes, hi. Hi, I'm ready. I'm just going to share my screen now. Okay, let me know if you can't see my screen.
Yeah, we can see.
Brilliant. Okay, so yeah, I'm going to be talking about optical solitons, so something a little different. And so what I want to do is first give a bit of background, which will be outlining what is a soliton, what are lithium nano waveguides, which is what we're using to simulate these solitons, and go over a little bit of previous work on these solitons, which will hopefully give a decent background to our model and some of our results that we've got so far. So firstly, to explain what a soliton is, which is a nonlinear pulse, I will first describe what a linear pulse is. So this animation shows a linear pulse, which, as you can see, disperses as it propagates. So due to linear interaction with the medium in which it propagates, it spreads out as it does so. And that's because of the difference in the group velocity of different frequency components of the pulse. Now, a soliton is, as I said, a nonlinear pulse, and because of the nonlinear interaction with the medium, it's possible to engineer a situation where the nonlinearity counteracts the linear dispersion, and you get a pulse that doesn't spread out as it propagates. Now, another way to visualize these animations is like a top-down view. So here, the pulse is propagating in Z, and it's spreading out in time, which is the transverse direction. Studied equation in which these solitons exist is the nonlinear Schrödinger equation, where this central term is the linear dispersive term, and the nonlinear term here is the Kerr term. And when these two cancel each other out, we find that the change in Z of the field is 0, and therefore you have a soliton. Now, we've been looking at lithium niobate nanowaveguides as a possible platform for seeing some solitons. And the reasons are that lithium niobate has a very strong quadratic nonlinear response and a very broad band transparency. Both of these are important for seeing the types of solitons that we're interested in. Now, in the last 10 years or so, it's become possible to make nano waveguides out of lithium niobate, where we see a significant field enhancement, which boosts the nonlinear response of light propagating in the waveguide, as well as the engineering the size and shape allows you to tune the dispersion felt by the light in the waveguide. And both of these are important for producing solitons in these systems. Now, most research on optical solitons has been done previously on Kerr solitons in silica fibers. So they've been shown to play a crucial role in supercontinuum generation, where in particular Raman shifting has been shown to broaden the supercontinuum. Now, of course, in lithium niobate, we have to consider the Chi2 nonlinear response, that's the quadratic nonlinear response. And previous work on such solitons in these systems have shown that these solitons have two components. So they have one pulse at the fundamental frequency and the second pulse at the second harmonic frequency. So that's twice the frequency. And both of these pulses propagate together, forming the soliton as they propagate in the waveguide. But crucially, in this previous work, Raman shift hasn't been considered in these two component solitons. So that brings us on to the model that we've come up with to model this system, which consists of a fundamental field and a second harmonic field coupled together. And I'll just explain the different terms in these equations. So these are the linear terms describing both the phase and group velocity mismatch between the two fields, as well as group velocity dispersion in each of the fields. Now these terms are the Chi2 nonlinear terms, and you can see they couple the two equations together. And these terms are the Kerr terms. You can see there's a self-Kerr and a cross-Kerr term in each equation. And finally, at the end here are the Raman terms, which we include as a perturbation to the solitons, and they have this functional form where this function R is the Raman response of the material. So I'm just showing here the Raman spectrum for lithium niobate compared with that for silica. You can see it's got quite a significant Raman response. So this system of equations without Raman is known to have soliton solutions of this form, where the psi f and psi s are the soliton profiles, and mu and nu are the soliton propagation constant and inverse velocity of the soliton. Now, starting with these solutions, we've managed to derive existence criteria for these solitons in such systems. So this first one is derived from a requirement that the system have a constant amplitude solution. And these other two are derived from requiring that both components of the soliton decay exponentially as you move away from the center of the soliton. So all these three together have been plotted on this diagram, where the shaded region for each shows where each criterion is satisfied. So where all three overlap, solitons can exist in the system. So this helps us link the dispersion parameters of a particular waveguide geometry with the soliton parameters that are allowed for that geometry. So in this particular system, we can have solitons with corresponding mu and nu values in this region. So now if we consider Raman shift theory, so if we add in the Raman response of the material, we treat that as a perturbation, so it's a small addition to our theory, and therefore we allow mu and nu, the soliton parameters, to vary slowly as the soliton propagates down the waveguide. Having done this, we've derived these shifts in mu and nu, and the functional form we find actually depends on both the soliton profiles and also the soliton parameters themselves. And doing this, we find, for example, a soliton starting here at this black circle in the mu-nu plane propagates along this trajectory due to the Raman shift. So this trajectory is shown by this red dotted line. And these shifts in mu and nu can allow us subsequently to find shifts in time and frequency of these pulses traveling in this waveguide. And these time and frequency shifts can be quite easily compared with simulated data, and that's what I'm showing here. So the colored plot where this column is the fundamental frequency for the spectral domain on the top and the time domain underneath. And what you can see here is the soliton shifts in frequency towards the longer wavelength. So you can think of constant shifting of components of the soliton towards longer wavelength. The energy is being lost to the material lattice. And as the soliton shifts in frequency, because different frequencies have different group velocities, it also shifts in velocity and therefore accelerates in the time domain. Our predictions of these shifts are shown as these black dashed lines, which are computed entirely independently. So you can see they correspond quite nicely with the simulated data. Now looking again at the mu-nu plane, the trajectory of the soliton here looks as though it's kind of coming towards the boundary of its existence here, marked by this dashed black line. And so that prompts the question of what happens as the soliton approaches the boundary of its own existence. So we've looked into this, and it seems that the soliton in this example approaches the boundary of its existence and actually recoils in the mu-nu plane. And simultaneously, it recoils in the second harmonic spectrum. And we can see, again, simulation lined up quite nicely with our predictions. At the same time, the energy in the soliton shifts towards the second harmonic component, and eventually a purely Kerr soliton is formed in the second harmonic, following the trajectory expected by a Kerr soliton, and this trajectory in the mu-nu plane, where this by this blue solid line, which shows that a Kerr soliton doesn't approach the boundary of its own existence, but a two-component soliton does, and allows for such interesting dynamics as what we can see here. So I'll just summarize and say that I've shown you the soliton existence criteria that we've derived. I've shown the two-component Raman shifting solitons with our simulation lining up nicely with our predictions. And I've shown a particular example where these two-component solitons are actually able to approach the boundary of their own existence and generate purely Kerr solitons. Thanks for listening. I'll be happy to answer any questions.
Cheers, Will. That was really interesting. We are running a tad behind, so perhaps we should ask the group one last time if there's any burning questions. But if not, let's take a bit of a break. I think we've got until 10 to 4 until the next scheduled talk. Yeah, thanks to all of the speakers for this session. And if we stay in the group as we did before, it might be a bit easier.
It's supposed to be Will Campbell talking, but I don't think he's going to be able to make it, so we might have to just press on and go with Alex van der Petch. So, yeah, so I'm chairing this session, which is now shorter. So, Alex, if you want to just go ahead and do your talk now, if that's okay.
Yeah, that's perfectly fine.
Great.
And I would share my screen. You see it?
Not quite yet.
It's just a short delay.
Yeah, now I see it. Yeah, it's fine.
Okay.
So yeah, Alex is basically going to be doing the last talk of the day then, concerning strontium ruthenate and its unconventional pairing in superconductor. Yeah, strontium ruthenate. Take away.
Yeah, I'm sorry I changed the title of my talk a slightly bit, but I think it's a bit more interesting than what I originally intended to do. So first of all, I want to thank my supervisor, Stephen Hayden, for coming up with the idea for this experiment and helping me with the experiment itself, as well as Manjun Zhu and Mechthild Enderle for experimental support, as well as Igor Mazen for theoretical support, and now directly jump in. So strontium ruthenate is an unconventional superconductor, which becomes superconducting at a temperature of about 1.5 Kelvin. It has the same structure as the high TC superconductors lanthanum, strontium, copper oxide at room temperature. So it's a layered tetragonal structure composed out of these ruthenium oxide octahedra, or layers of those ruthenium octahedra sandwiched between strontium atoms. And take in mind, there are two different oxygen sites, the inner end plane and outer plane. I will mention later. In its normal state, it's a Fermi liquid, good Fermi liquid, which shows correlations and additionally ferro and antiferromagnetic fluctuations, but it's not magnetically ordered. And however, its superconducting state is a bit odd. So it, for example, shows time versus symmetry breaking. And really early on, due to the time versus symmetry breaking and due to ferromagnetism, it was seen as an analogon to the A phase of helium-3, maybe a couple of ones might know you, or a chiral triplet superconductor. But what is a chiral triplet superconductor? So the normal superconductor we normally work with are singlets. So for example, SMD wave, where The spins on opposite sides of the Fermi surface are coupled with opposite spin sign, whereas in the triplet states, they have the same spin direction and can have an additional orbital moment. That's the first part. But more interesting for us, okay, next thing is that its gap function is actually not a scalar like in a singlet, but is something defined by some so-called D vector, which I will come to in a sec. And for us, most interesting is the spin susceptibility in such system, whereas in a singlet system, the spin susceptibility at 0 temperature and field goes to 0. For example, shown here for an S-wave superconductor, so the temperature dependence, which is called Yoshida function, or analog for a D-wave, which both go to 0. In a triplet superconductor, this depends on the triplet state and the alignment of the magnetic field, so the H vector corresponding to the alignment of its D vector. So it depends on the field. For example, if we have the D vector in plane on a tetragonal system and the field is in plane, we would see a drop to about half the normal state, so spin susceptibility. Whereas if there's no, if the field is perpendicular to the D vector, we would see no change at all between the normal state, spin susceptibility, and in its superconducting state. However, the spin susceptibility is not a necessarily easy thing, because if we want to measure, normally measure susceptibility on a superconducting material, for example in a squid, what is actually measured is the magnetic screening, the screening by the superconducting screening currents, rather than the spin susceptibility, which is coupled to the electronic density of states and reduces due to the pairing of electrons. But there are two possible probes which can do that, which are both bulk probes. One is the nuclear magnetic resonance, which magnetization or shifts of nuclear resonances, and polarized neutron scattering. A tiny thing to mention here is, even if we want to measure spin susceptibility, what we actually measure is in both a sum of different susceptibilities, even for NMR, even a bit worse. And this was already seen in the first polarized neutron scattering experiment, where they looked for superconductivity by Sean Bedford in magnesium silicide, where they see a nice S-wave drop or Yoshida function, but see a remaining part due to orbital contribution via magnetism and density of states introduced by magnetic field. But back to strontium mufenate. So as I mentioned before, if you have a triplet state where the D vector is perpendicular to an applied field, you would see no drop. And such a thing has been observed in NMR night shift measurements, where they went into the superconducting state, which is marked about here. And on two different oxygen sites, they don't saw a change in its night shift, so which would support such a state out of plane. And this I term basically gives the time versus symmetry breaking. And there has been another experiment by a couple of years later in polarized neutron scattering, and there as well has seen no significant change in the susceptibility and was interpreted likewise. However, I will give you a new study on basically the same setup, but at half the size of the field, about 1/3 of BC2. Where we see that field dependence of spin susceptibility can make quite a lot different, and now we observe a drop. But what did we do at the experiment? Recently, the group around Stuart Brown observed that in strain strontium mufenate, but even at 0 strain, which is marked around here, there's actually a change in NMR between the normal state and the superconducting state, which means that there's actually for fields applied in plane a change in the spin susceptibility, and these should be then also observable in neutron scattering. So, but what does polarized neutron scattering actually measures? So it can directly measure magnetization density in a system, which it does by which we do by measuring a Bragg reflection, where we look at the interference between nuclear scattering and magnetic scattering, where the sign term over here depends on the direction of the neutron spin towards the magnetization inside our sample. The problem is we have over here, the signal is really small. It's in the order of, or the difference between those two from unity, the ratio of those two from unity is in the order of a few times 10 to the minus 4. And when we then want good statistics, we need something like 10 to the power of 9, 10 to the power of 10 counts. So our experiment is actually limited, or this whole work is limited by counting time and a statistic rather than environment, for example, which has to be taken into account. And so our problem is we couldn't take much data, but we could at least take one in the normal state and one at low temperature. And what we observe is actually a drop by about 1/3 of the normal state susceptibility. The thing which we'll take in mind, I will explain in a second, is that the experiment was performed in a mixed state. So we have additional density of states coming from field-induced density of states or flux vortices. But coming back to our dependence, we would basically be able to fit in a S-wave or nodal model, but because of the lack of data, that doesn't really make too much sense. But if we think about at least field dependence, what we get is that if we include field dependence and the shift of TC due to the field, that the drop in the previous experiment at 1 Tesla, which didn't observe anything, can be actually well understood by a really small drop and low statistics. But look at a bit more interesting field dependence. In general, the field dependence would be easy. We can have a nodal model which drops down quite far, which is about a square root dependence, or a D-wave model, and an isotropic gap model, which is kind of linear. However, it's not that easy because, as I mentioned before, we're not only measuring the spin susceptibility, but extra components. For example, the orbital contribution, which is currently a bit under discussion. So DFT suggests about 11% of the normal state value, so around here, whereas DFT says orbital fluctuation can even enhance it to 22%. And another factor which goes in is the correlation, which enhances susceptibility, where we found a Wilson ratio of about 1.5 to 2. If we take an orbit of the orbital term and correct for the Stoner enhancement, what we actually get is a bit different values. So we see about 25% or reduction to 25% of the normal state value for a nodal model, and about 55% of the normal state as residual value, so for 0 field and 0 temperature for a isotropic model. However, if we first of all compare that to other measures which should also see density of state related to density of state, for example, heat capacity, electric thermal heat capacity, they at least are lower, which might be due to stronger orbital contributions. However, they also see a relatively sharp drop down, which follows the square root. So we can kind of say that it seems to be a nodal model. However, the other system, NMR, sees an even larger drop, which I assume is due to different orbital contributions, because they're measuring first of all on oxygen sites rather than as we did on ruthenium sites. Furthermore, subtracting and shifting for orbital terms is really hard in NMR, as basically as a recent paper shown, or a recent NMR paper shown, where slightly misalignment seems to change the signal quite strongly, as well as a subtraction is based on this old figure where on the linear fits on this old diagram, which we know now is a bit outdated due to because it also depends on the orbital contribution of the spin susceptibility. But summarize the general understanding of strontium glufonate. So as we saw when NMR saw a drop in the spin susceptibility, it means that first of all, if it's a triplet state, then the D vector can't be out of plane. So the origin Cairo state doesn't work. The D vector must be in plane. Furthermore, recent experiment we observed time versus symmetry breaking. which would support a 2-order parameter state, and our field depend and tends to work towards and recent experiment vertical line nodes. However, the parameters in the system seems to be, or the electronic parameters seems to be quite interesting in the system. So it can be that even states which are usually metric, for example, S-wave, show nodes, as for example calculated here last year. And to preserve the time with the symmetry breaking and alongside those accidental degeneracies in energetic levels, a variety of states has been proposed, for example, S plus D, D plus G, a helical triplet state, which might work with our data, but not with the NMR data, or even a singlet, and in combination with a triplet state. And then I would finish up with that. So it's still really, the discussion is really open and interesting to follow. Thanks for your attention. And thank you. Any questions?
Cheers, Alex. Thanks very much. Yeah, so the session is now open for questions if anyone does want to. Yeah, Matt Curtis, if you would like to unmute yourself.
Hey there. When you were suggesting the possible states, where did you generate the list from?
So first of all, I actually have a list of possible states which are allowed for a triplet state with spin orbit coupling, so the material is strongly spin orbit coupled, where is a large variety of states possible. However, first of all those triplet states, these are the state is here the triplet state, and all with a D vector, which is defined by this by the vector component here. With that component goes out because we observed on the other side, because it's a layer structure, all these KZ components seems to be quite unreasonable. So basically as singlet states, these terms remain, and for triplet, effectively these 4 states are the ones which are most reasonable. Otherwise, there's a lot of theoretical calculations within the last year, basically, where they looked at the effect of or the competing between spin orbit coupling and correlations. And what they basically get is that the energy levels and are really, for a lot of those states, are really close to each other, and minor changes in spin orbit coupling, strain, or can easily go from one to the other. And that is a 2-order parameter state was recently supported by measurements under strain, where the time of the symmetry breaking was turned up at lower temperature and superconductivity. So they see basically that strain can kind of decouple the 2 states.
Oh,
does it explain your question?
Okay, if anyone else has got any more questions, feel free. Otherwise, I'll ask a very amateur question. So you said somewhere in your presentation that NMR and PNS are sort of complementary in that they show different sides. So what actually was your study? Was it both, or did you just sort of...
No, we did the polarized neutron scattering, and it's not necessarily complementary. So the problem is NMR normally measures a nuclear excitation, so it needs a nuclear isotope which is magnetic. And there is in strontium rutheniate 2 options which might be interesting, so ruthenium or oxygen. However, from the ruthenium side, the signal would be really small and the energies to excite it would be really high. However, as I might have mentioned before, the previous experiment suffered from sample heating, so measuring ruthenium might even be impossible. So they only looked on oxygen 17 excitations. For us, that we looked on the ruthenium side, is a bit more complicated. These depend on a Q. So what we actually measure is a Bragg reflection. And depending on where we're in Q space, different terms cancel, and we use the Bragg reflection where only, or nearly purely their signal from ruthenium, whereas the oxygen sites, due to symmetry, cancel out.
Okay.
So
Thank
it's,
you very
and yeah, and another point which I haven't discussed too long is that we directly just measure some of susceptibility, whereas in NMR, spin orbital have different probability factor, proportionality factor, and therefore go in a bit differently.
Okay. Thank you very much. I don't know if anyone else has got any more questions. If not, I think that concludes that very short session.
So I'm pleased to say the best talk was to Liam. Okay.
Yay.
Thank you. Thank you for voting. I'll send the bribes over soon. Don't worry, guys.
And the best posters were a tie, Lucas and Will Lukin. So we'll give you some vouchers. And the most important poll then is the best background, I guess.
Yeah, so I'll move on to...
Right, are you going to put your backgrounds? Oh, people are putting backgrounds.
Yeah, so this is
quick.
This is a short list.
Get your background up.
Short list from the panel. So apologies if you have a funky background and it's not made it to the short list. If you are on the short list, then you might want to put up your background so that people can start voting for you. Oh, wow. So we've got 29 people who have voted for this. So 2 people abstained from the last vote. So only 27 voted.
Are the votes still coming in now?
Well, no, it's pretty much done now, I think.
Okay. Well,
so
why don't you can have the honour of announcing.
Well, I'm going to attempt to publish the results of this one. Yeah, I can share the results of this one. Yeah.
Oh,
very good.
Runaway winner.
You've made Tom very happy, everyone. He's busy
I
writing
was waiting for
thesis,
Tom, not
so-
Charlie. Can I retract
Yeah.
my vote, please?
Charlie, can you actually tell who is that person behind you?
It's Tom. He's busy writing his thesis, so I thought he's just behind me. Tom, come in. Just come in.
Right space.
Actually, it's detecting it's a real person and not showing him. Yeah. Fantastic. Okay, so all that remains to do then, to be done, is to thank Jared and Amy for organising things, and Tom, of course, as well for the polling, and Joanna. Yeah.
We have a small token of our appreciation for Jared and Amy, which will probably be in the post, I guess.
Anyway, okay, so thank everybody and the speakers as well for some very nice talks and posters and backgrounds. Okay.
Thank you, everybody.
Thank you, everybody.
Thanks, everyone.
Take care. Thank you.
Thank you very much.
Bye.